That I have the interview.
Yeah.
Okay, so I would like to thank everybody for participating today and to make actually this event possible. And I don't want to talk too much because as Italian, I don't always too much. So first of all, I would like to say how we got here. It was just by chance speaking with Laura a few years ago about our prospective research, and she got awarded a grant from the European Union to run a multi-site study on creatine deficiency disorders with for establishing functional biomarker. And during the discussions about we do functional biomarker as well, was well, unfortunately or fortunately, the disorder is very rare, and we have only few patients. And so I said, well, we should come to Boston. That's how we started. How can I come to Boston? Well, I don't know, but we should do in Boston, because in Boston, at Children's Hospital, actually, we are really devoted to establish biomarker, run, be ready for clinical trials, develop treatment, test treatment. And so that's how we started. My lab does research on rare neurodevelopmental disorders, but does not work on CTD, CTDs until now. And I do not run functional NIRS. I use actually EEG and visual evoked potential, but we're not so far apart. And so we started to say, what would be necessary? Well, we need a clinician. So we found Irene. And then we will need a system to acquire, to run this experiment. We talked a little bit around with some collaborators, but in the end, we decided that we could make an investment and actually establish our own pilot study with our own machine. And we were very lucky to have Heidi and Sangeetha to brainstorm with us and find a way to purchase a system for us. And they applied to the Ludwig Foundation, and they said yes. And so, as a magic, we were in the machine, and at the same time, the hospital, Boston Children's Hospital, was very open-minded to help us to launch this multi-site study, and they gave it the ICCPR, gave us a pilot funding for 2 years for $80,000 that allow us to do the work. And so now we are writing the IRB. We already collaborate with NIH because in reality there is already a study similar to ours at NIH. We are going to share the stimuli to be sure that we are collecting the same type of data so we can pull them together. So when you put this energy together, you can reach whatever you want. So today, this is an event to talk about where we are with the research for creatine deficiency disorders in terms of both of clinical and preclinical and where we want to go. And so I would like to have first Mustafa Sahin to open talks to discuss a little bit, to present what we are doing here at Children's Hospital for translational research. Thank you so much. Thank you everybody for being here. A special thanks to Katie because helped us to make this possible, and everybody else who made this day and future days possible. Thank you, Lisa. And then for the for the people who are at home, so we have people connected. If you have questions, you can write the questions in the Q&A, and then Katie will help us in reading such questions. The webinar is going to be recorded and then can be shared to everybody for watching.
Well, thank you so much for having me. It's so nice to see you. My name is...
Yeah, you're good.
Okay, great. My name is Mustafa Sahin. I'm a professor of neurology here, and I run the Translational Neuroscience Center. I also am the PI of the Intellectual and Developmental Disability Research Center, and I work with Michela and Irina and many others in this room. So it's my pleasure to give you just a maybe 10-minute summary of some of the efforts that we've built here to accelerate development of therapies for children with neurodevelopmental disorders. This is part of our IDDRC center, and it's also funded by a philanthropist named Zander, So it's named after her husband, Zander Translational Neuroscience Center. The goal of this center is to improve the lives of children with brain disorders by fostering timely and efficient translational research based on the core principles of scientific rigor, collaboration, diversity, equity, and inclusion. We obviously have very good clinicians here. We have very good basic scientists, but actually making that bridge between the two sides have been something we've been aspiring for. This is why we built this center about 12 years ago now. Our focus is on therapeutic development for genetically defined disorders of pediatric onset in which neurodevelopmental phenotypes, so intellectual disability, autism, epilepsy, are the core features. And where there's no effective treatment and there's a patient community that is desiring of therapeutic options. So if you have all those components together, we would love to work with you. There are 4 core missions of the center. One, accelerate the translation of therapies. The second is to collaborate, reduce the boundaries between departments and divisions, reduce the boundaries between basic scientists and clinicians, and reduce the boundaries between academia and industry. Another core feature is to educate the future leaders of this field who are going to be running the clinical trials and communicate this model to other centers, both in the United States and across the globe. These are some of my colleagues that I have the pleasure of working with. They're an incredibly talented group of people with diverse expertise and backgrounds. Here is the key discovery cycle that we base our center on. We always start with the patients. In most cases, these are genetically defined cohorts of patients. For various reasons, people from all over the world come to us, the children's, for the care of their children. A lot of times because we do research on those disorders, not just for the clinical care. Once we have a genetically defined patient cohort, we then try to develop a characterization, natural history of these disorders, and also work very hard to develop biomarkers, which we believe are crucial to accelerating clinical trials in these types of disorders. And then almost always we use preclinical models. These are cellular models. In the past, most of these were mouse or rat neurons, but more and more we're using human neurons derived from stem cells. Then we have to, in many cases, go into animal models if they're appropriate animal models, and then go into clinical trials with the knowledge that we've developed from the cell-based and animal models. As I show here, it is likely to be a circle that we go through several times. The first attempts may not be successful in getting effective therapies, but we need to iterate and build safer and more effective therapies as we go forward. It's important to note that sometimes we also learn things from clinical trials, which make us go back to the basic science and understand the actual mechanism of the disease. Our facilities are on 2 campuses. The facilities that have to do with basic science are mostly on this Longwood campus, but we also have a campus about half a mile away called the Brain Mind Behavior to Brookline Place campus, where we have a building that's just recently built and opened, just really focuses on neurodevelopmental disorders, where we have many of our cores. In that facility on the 7th floor, we now have a research unit we just opened this fall, where we have 3 exam rooms, 1 consult room, a pharmacy, blood draw, EEG and MRI nearby, just for neurodevelopmental disorders. Here's a visual that I'm very proud of. These are some of the patient advocacy groups and funding agencies that we've had the pleasure of working with so far. And in some cases, there's multiple patient advocacy groups in the same disorder, and we've been able to collaborate with multiple groups and leverage the resources of each group. I'm just going to very briefly go through our cores and services. We've developed a human neuron core because human neurons that are developed from stem cells are becoming an extremely important tool to test certain hypotheses, to test certain compounds or treatments in cell culture before we go into the patients. So we have, with funding from Mass Life Sciences and some philanthropic groups, we built this core that has 10 people working full-time to have standard operating procedures to develop different subtypes of neurons for various disorders. We also have a biorepository with where we collect samples. This includes blood, cerebrospinal fluid, urine, skin biopsies from patients with various disorders that can be in the future used to test hypotheses related to this disease. We've tried to standardize basically all the assessments that are possible. So in the past, people would go out and find their own psychologist for every trial that's being done. Instead, we've developed a core service that provides research quality neuropsychological assessments for all of these disorders. So we have a core now that can do autism testing, we can do cognitive testing, adaptive behavior testing, language testing over and over again. We have a neurophysiology core where we can do high density EEG, eye tracking, and other kinds of functional assessments. Importantly, this core works closely with Michela's animal behavior and physiology core, so we can actually go back and forth between animal models and the patients that we see in this core. We have a translational genomics core that's run by a geneticist, Maya Chopra, who came from Australia. And she has built a team that can curate sequencing expertise. But importantly, she's also led an effort to look at the framework of evaluating different Mendelian neurodevelopmental disorders that might be appropriate for gene-based therapies. What are the gaps before we get to gene-based therapies that we have to address? And some of these gaps are at the biological side, so the dosage of the gene, the expression of the gene, which cell types we have to go into. Do we know all of these basic biology about the disorder? Some of these gaps are on the clinical side. Do we know the natural history of the disorder? When is it reversible? When is it not reversible? Are there any biomarkers that can be utilized for clinical trial? Are there ethical issues that might have to be addressed before a clinical trial is addressed? So we've published a paper called Gene Target that actually gives some metrics as to where each disease might be along those different criteria. We also have a medicinal chemistry core led by Jed Hobbs, who used to work at Merck, who brings his expertise in pharmacology, pharmacokinetics, pharmacodynamics, and allows us to make new molecules in an academic setting, just like sometimes the pharma would be able to do. These are some of the clinical trials that are ongoing right now. One of the big hurdles in translational research was that we didn't have an infrastructure that accelerated regulatory issues. Could we go through the IRB in a efficient way? Could we get an IND for a clinical trial in an efficient way? Could we have agreements with pharma or CROs in an efficient way? So we built a clinical research operations core that has really accelerated the onset, execution, and analysis of these trials. So we have currently 57 ongoing clinical trials that are under the auspices of this core. This is just another slide showing some of the criteria by which we've been looking at single gene disorders. As I mentioned, some of them are specific to the biology of the disease, but others where the bottleneck is not the biology of the disease, but it's actually whether a clinical trial is feasible and can be performed. So I'll stop here. I just want to give you a few minutes of an introduction about the infrastructure we built here. We have a website, rsctnc.org, that you can get more information. And I won't be able to stay for the whole meeting, but I'm really glad that this meeting is going on. I look forward to the collaboration that will come out. Thank you for coming.
Questions in the room?
I do. Thank you for that. That was very informative. I actually was interested in your some of your core services as it pertains to biobanking. I just want to understand what your typical practices were in terms of collecting patient samples, deriving them into fibroblasts and/or iPSCs, and how might an association like ours consider something like that?
We actually work with a lot of patient advocacy organizations to, let's say, make iPSCs from the patients. We just had we have a couple of papers that are already published working with CTD-NIMH-NIH disorder organization called Lula Foundation. With an agreement, we collected from the clinician who sees these patients a subset of fibroblasts. We made iPSCs. We corrected the mutation in some of them, so we have isogenic controls. And we openly share them with the foundation. So they can actually give it to anyone who wants to use it academic setting or in the pharmacy.
So do you have a mechanism to collect samples directly from patients?
Yes, we collect from patients essentially anywhere in the world because we collected patients in Europe, for instance, using blood rather than fibroblasts. So we have an IRB protocol that covers all diseases. It's not disease specific. We have coordinators. If a patient is an inpatient or outpatient at Boston Children's, the coordinator can go and send them. We have a human neuron core that can take the fibroblast biopsy and dissociate the cells and grow the cultures that are necessary. We work with the Harvard Stem Cell Institute across the river to make the iPSC, and then we make the CRISPR connections ourselves.
That's great. Maybe we can connect offline. I'd love to hear about the funding for something like this and understanding how the mechanisms for that might work. The other question that I had was regarding the clinical trials you have underway. I was wondering if you could talk about your experience working with the patient organization. What do you see their role as being, and how you set up these relationships?
So we have, a number of different opportunities. We just had the third patient ever to get the MECP2 gene injected using the viral therapy interventrically using a neurosurgical approach here at Boston Children's. I think 10 days ago. So, that's the sort of tip of the iceberg, if you will, but we have a number of natural history studies. For instance, I work with 3 patient advocacy groups on TSC NIMH-NIH. We got a NIH grant. The patient advocacy groups help enroll patients for that grant. Our goal was to get 100 patients and do every year phenotyping of those patients. So we actually have a very deep phenotyping of those patients. And in fact, Jaguar Therapeutics, which is working on a gene therapy for SHANK3, just announced that they're going to use our natural history data just from our study as the IND enabling historical natural history study. So they're literally taking academic data and giving it to the FDA as part of their IND.
And how far do you see your center being pivotal in taking this to market, so to speak?
Well, Jaguar is going to use our 5 centers that was necessary to generate the data as their clinical trial sites. So, they are making the IAB, they are making the gene therapy, but we'll be in that trial. Thank you very much.
As you can see, this we have Mustafa here because the idea is to show you more what is the possibility, and I think having already studied starting there could be implemented or expanded. To reach out to them directly. Okay, so now we do it. Let me switch, and we want to have the family perspective, the patient perspective for the disorder, because I think we cannot fully understand why we have to do this until you really hear from the family, right? The doctor will never know fully what it means to be affected by a disorder. You can understand the presentation, but living every single day is something else. And so I think that we are very lucky today to have a different perspective from the foundation and family. So I don't want to talk more. We will start with Celeste.
Hey, good afternoon. Please bear with me with my voice. I have the privilege of speaking today as a mom. I have an 11-year-old son. He'll be 12 in April, and he has CTD. So I just want to start off by giving you a glimpse of what it's like, what our life is like to live with Levi on a daily basis. I actually have 4 kiddos. I have a 9-year-old girl, I have a 2-year-old boy, and I have a 1-year-old boy, in addition to Levi. So Levi is originally from Ukraine, and the adoption process, we were there for 38 days. So I titled this slide, A Whole New World, because we were just thrust into it. My background is special education, and my husband's background is civil engineering. So I had a little bit more kind of under me than he did. And when we went, we were told he had one thing. We were told he had cerebral palsy. Immediately when I first met him, my special ed background kicked in. I knew there was more to the picture. So just kind of oversight with the special educator background versus the engineer. You have the theoretical versus the practical, the big picture versus the easy fix, straight to the solution. So some things that we deal with on a day-to-day basis. Levi's nonverbal. He has a communication device. He knows how to say 3 words, help, up, and mama. He has some signs, sound, and word approximations. And he has lots of screens. So he has happy screens, sad screens, mad screens. We can tell the difference, but the general public, they just know a kid's screen. He needs constant supervision. He has no safety awareness whatsoever. We've installed home modifications in our home. We have to be very, very careful when we go out in the community. He has a wheelchair stroller to help with that. He is a runner. A lot of people see him get up out of his wheelchair stroller and they're like, wait, he can walk. Oh, yes, he can run. His behaviors. So for us, for our family, for Levi, CTD manifests a lot in his behaviors. We have a lot of tantrums, and they can be a simple protest to tantrums upwards of 45 minutes plus, to the point where he loses what he's upset about and he just can't get it back. We see a lot of self-injurious behaviors, headbanging, hitting his head with his wrist, biting himself, aggression, malicious and non-malicious. They'll push, hit, pull, throw things. Sometimes he's just wanting to interact with his siblings, whereas peers, he just doesn't know how. And that's where he's at, his form of communication. He likes to go limp or wet noodle a lot. And so, as he's getting older, then he's getting stronger and bigger. And we're not. So it's getting a little more challenging to lift him and get him up the stairs to bed and out of a parking lot, things like that. He's extremely impulsive and hyperactive. Our developmental beat is like, if anybody saw his med list, they would be like, wait a minute. But just in the way the metabolizing the meds and the way that, they affect him, this is what he needs for baseline, and oftentimes we hear from school and we're like, we're doing all we can. Like, he's already on a significant amount just to maintain this baseline. I like to call it Levi proofing. So we have to make sure everything is Levi proofed, whether it's at home or whether we're going somewhere to stay in a hotel, grandparents' house, no matter what. So we have shatter resistant windows, every window that he has access to, even sliding glass doors. We have a fence around our backyard, a gate around our front porch. We had a kitchen island when we moved into our house, and we had them put half walls around it because at least a visual barrier gives us that couple-second jump to get to him. Of course, he can open the door and scale it, but it gives us that extra jump. We have different locks. His bedroom's on the 2nd floor, so we have the locks to where you can't lift the window. In addition to the shockproof, our sliding glass door has the lock up top. We have multiple locks on our front door, a security system. So his room is Levi proof. He has his bed in there, all of his stuff's in his closet, which stays locked. And then he has soft animals, which he loves. So he has a ball in there, but nothing hard, nothing that could cause any damage or anything like that. And there's a baby camera mounted on the ceiling just so we can have eyes on him. We've also turned his doorknob around to keep him safe at night, as well as so that we're able to sleep and not have to worry about things. Diaper changing is like wrestling an alligator, if you can imagine. And so he's incontinent, and so that provides its own challenges. We turn to find one-piece pajamas that are big enough for him. We can turn around and zip in the back so that he can't disrobe because he can take things off. He needs full prompting for self-care. So we're still giving him those baths. We're still wiping him up after meal times. We monitor him while he's eating. He doesn't stuff and he doesn't gag. Recently, we've seen an increase in behaviors. It's a behavior, but when he gets super excited about something or when he doesn't like something, he just starts gagging, and then sometimes he'll make himself throw up. And so that can prove to be a challenge. We have to always anticipate, where's he going, what's he gonna do, is he gonna grab siblings? Especially with the little kiddos, he doesn't realize his own strength. So when he grabs the 1-year-old's arm, we have to make sure we're pretty close. But also for tantrums and for overstimulation. We know going out to a crowded restaurant is going to be overstimulating and cause behaviors. So we have some strategies that we use to try to help mitigate that. It's not ideal, and there's a lot of mom guilt that comes with it. But it's things that we have to do just to kind of, because we still want to be a family. We have to try to figure out what hurts or what's not feeling good or what he's upset about. It's a guessing game. He can't tell me. He localizes pain. So he'll come and he'll point to his hand if he just got bit by an ant outside. And then we, like I said, try to plan to be really as proactive as possible. Being okay with the mess. My house stays a mess, and I'm learning to be okay with it. Relationships. This is one that we really struggle with sometimes because the general public doesn't understand. They don't understand Levi. They don't understand what we're trying to do. Sometimes family members have well intentions, and then we have to kind of work through situations, and then dealing with others' opinions and reactions, and their ignorance. A lot of people can be quite rude and sometimes not intended. I remember on our way home from Ukraine, it was a 10.5-hour flight. Levi screamed 10 hours. And it was, people on the plane were not nice. I completely get it. I totally understand it. But we were doing everything we could. And the same when we go out in the community, when he gets overstimulated and he's tantruming, we're trying to fix the situation the best we can. But sometimes until he just wears himself out or gets distracted, he's not gonna calm down. And then working through lack of empathy. So just real quick, our CTD diagnosis gave us some closure because we have the diagnosis, but it didn't decrease any of the stress working. Job changes, day-to-day changes. I went from full-time to part-time to now from home. Thankfully, my husband's job is flexible as well. Doctor's appointments, all over the place, therapies, weekly. We're always going somewhere, having somebody in the house. We recently made the decision to pause ABA because it was just a lot. He doesn't get home till 4:30, and then somebody else in the house at that witching hour. He's tired, everybody's tired. So it's just kind of, you have to figure out that balancing act. It's a lot of decisions. And again, that mom guilt creeps in. Am I doing everything I can to help him be the best that he can be? Lifestyle. So much more preparation goes into going places, stores, church, even riding in the car. We don't like to stop at a stoplight. We don't like to order at a drive-through. And just trying to be prepared. Meds, communication device, snacks, diapers, iPad, wheelchair, or his harness. When we're traveling, how do we make it Levi-proof? We're going to a new place at the beach this summer. I've never been there. I'm gonna have to go in before he even gets out of the car and just make sure we've got breakables out of the way and stuff. And a plan to deal with behaviors. Often Phil and I kind of divide and conquer because we have the 3 other kiddos, and then so somebody usually has to be on Levi and somebody's on the other 3 kiddos. Breakthroughs and burnouts. We've learned to celebrate the small things. It's amazing when somebody from outside, points out progress that we can't see because we're in the thick of it. Burnout, big emotions, stress, and guilt are very real, and we're learning that it's okay. It's so hard to just be in that constant mode of working through behaviors. Even with my background in working with behaviors for years, advocacy and analogies. So our focus has shifted from dwelling to advocating, for what Levi needs and for the greater CCDS community, in our lives. I was talking to Phil the other night, and he came up with this analogy, and I think it fits very well. Our lives are like a construction site. It's often messy, but we're making progress. And what's in the toolbox is always changing. Real quick, so this is a picture of the day we came home with Levi. Paisley, she was 27 months old. She had been an only child. She was really quiet, just a sweet little girl. We turned her world upside down and inside out within 5 minutes. I was talking to her. She said it used to be the three of us in call. And then she said it's turned into a crazy loud world. We really have to work hard on teaching boundaries. With a lot of Levi's behaviors, with him wanting to interact, with the pulling the hair and hitting, we want her to know that's how Levi's communicating. We're working through it, but it's not okay. I don't want her to grow up and know that it's okay for anybody to exhibit those behaviors towards her, right? It's shaped who she is. She has the biggest heart. She has the most empathy. She's able to identify, with a lot of kiddos at her school that have special needs. She is so wise beyond her years. When we were doing ADA, she would be like a little mini behavioral therapist. She would say, okay, Levi, this first this, then this. And what she's learned, I asked her, she said she's learned how to deal with his screaming, his pulling hair. She said she tries to play with him and she's 9, she's almost 10. So she's got a life ahead of her, but and she's also often used the skills from behavioral therapy and speech and OT, like I said, with the first and individuals, to when she's playing with him. Well, then we've had some new additions as well. And so with Blaine, so Paisley was 27. Levi came from an orphanage where he had been his entire life. So with Blaine, when he was born, Levi wasn't really interested in him and didn't really seem to understand until he started moving and talking. And I look back now and I think that's because he had never been around a baby. With Gabriel, he's been more interested and curious. Sometimes when he cries, it's really sweet. Those moments, it makes me, he's got so much in there. His receptive is huge. And for him to bring a baby, the cup or the passy whenever he's crying versus a block, or, to me that shows some connection. So boundaries, we really try to work on, like I said, boundaries. He's not aware of his own strength. He really wants to interact with others. He doesn't know how. He lays on, pushes on, pulls on. Sharing toys is a big one. And now is getting quite interesting with a 2.5-year-old. They kind of take from each other and hit each other. I'm like, well, okay. Attention. We've got to do better at this, but we have to be intentional in finding that balance of spending time with everybody. Teaching his siblings about Levi and his differences in communicating and learning. And then we're trying to figure out the differences between discipline and correction, and trying to help our other 3 understand, those differences. And then organized chaos, getting used to the fluidity, acknowledging that I've recently started doing this, like, this is going to be crazy and it's okay. Like, we're going to struggle, it's okay. And then constantly just working through the stress levels, burnout and guilt. Phil and I had the opportunity to go to Salt Lake in the fall, just us, for the first time. I can't even tell you when. And we realized how much that we really needed that time just to kind of step away. So while I've shared a lot about Levi, our community there's so much variability within the community with how symptoms affect our kiddos. GI is a lot more prevalent in some kiddos. Seizures are a huge issue for some of our kiddos. So it's important as we, push towards clinical trials and as we look for these biomarkers, there's variability in the symptoms as well as the severity, and it's important to keep that in mind. But when you walk into a room full of kiddos with creatine deficiencies, you can see that common thread. And so there's often mild to moderate to significant delays. Seizures are controlled, not controlled. No behaviors to significant behaviors, fully verbal to non-verbal. And lastly, this was taking this past December, and it just kind of shows me the wonder in his eyes. I love this picture. But all of the symptoms that we struggle with are on the left side. And so I tried to think, what a treatment, how would that help us? What would we wish for to help us? I'd love for it to decrease crazy amount of medication that my kiddo is on. decrease his emotional dysregulation, his self-injurious behaviors, aggression, and impulsivity. I want him to communicate in the moment what he needs so he doesn't get to that level of frustration, how he feels or what hurts, to interact appropriately with others. I want him to have the cognitive ability to potty train and to do some self-care skills to increase his self-dignity and self-esteem. And all of that would help reduce caregiver burnout and stress. But this list looks very different for each family in our community. And it could change for us, but this is where we're at now. So that's a little glimpse into our lived experiences.
Hi, my name is Ellie Wallis, and I'm 17, and this is my family. So Sam is my older sister. She's 20 years old. And then I have two little brothers. The one in the middle is Bubba, he's 16, and then he's 12. So Sam and Louie have GAMT, and me and Bubba don't. So I'm a senior in high school, and I've been writing a lot of essays for college applications and scholarships and stuff like that. And one of the essays that I wrote was about Sam and like my experience like being her sibling. And so I'm gonna share that essay with you guys today. My sister has been intellectually disabled since birth. Her name is Sam, and she has a rare genetic disorder called guanidinoacetate methyltransferase GAMT deficiency, a creatine deficiency disorder that mainly affects her brain. My parents didn't know what was causing Sam's developmental delays until she was 5 years old and started having staring spells. When she was finally diagnosed and began treatment, it was too late. The damage had been done, and there was no turning back the clock. I'm not sure when I realized my sister was disabled. It could have been one of the many times I saw her interacting with children her age and her complete lack of social awareness. Maybe it was when, at the age of 10, she decided to take off her clothes and jump into our inflatable pool naked and screaming with my cousins, who were there looking completely stunned. Sam is 3 years older than me, but when I was young, I didn't think anything of her behaving younger than me. I didn't know anything different. I played with her and didn't process her lack of speech or the constant absence seizures causing her eyes to roll back into her head. I remember the first time I saw her have a convulsive seizure. We had just moved into a new house, and Sam and I shared a room. I was about 7 years old and trying to fall asleep when I heard rapid choking noises in the bed next to me. Without giving it a second thought, I ran out of the bedroom, screaming to my parents for help. This was the first time I had experienced true terror. I was crying uncontrollably, not sure what was happening, and terrified for my sister's life. Luckily, she was all right, but from that point onward, it was apparent to me that my sister was different. During my elementary years, I was embarrassed of my sister. I was scared that people wouldn't want to be friends with me because they would see Sam. So I would usually only go to my friends' houses, or just have people over when Sam was in bed. My mom was the president of the charity Association for Creatine Deficiency at the time. And whenever she wanted me to do something like pass out flyers for a fundraiser at school, I was mortified. Just thinking of telling my friends what ACD made my cheeks turn beet red. I felt guilty for being short with Sam and frustrated that I couldn't form a relationship with her. I didn't know anybody else with a disabled sibling, so I felt very alone in my experience. When I entered high school as a sophomore, I took peer tutoring as one of my classes. I got to help the kids in the special education classes one-on-one and develop relationships with them. And it was in that class that I realized how empathetic my peers are to disabled kids. I would see kids in the hall high-fiving Isaac, a boy with Down syndrome, as they passed by. And girls would sit next to Ninda, a boy with autism, at lunch. It helped me get over my fear of being judged by my friends, because it was clear that nobody was judging these kids. My sister is no longer an embarrassment to me, but a source of strength and perspective. When I think about Sam, I know that my problems are small, I focus on the things I'm grateful for. Now I tell my friends about ACD. I even nominated ACD for my high school's annual holiday fundraiser this year. I'm a lot more patient with Sam, and I take the time to understand where she's coming from and why sometimes she acts out. So, having a sister with special needs can be really hard. The seizures are scary, the temper tantrums are frustrating, and the communication is almost non-existent. Kids with GAMT need a better treatment. Luckily, Sam can take creatine every day, but she's still suffering neurological damage from before her diagnosis. Her JA is never normal, and she continues to have seizures. There are about 100 photos like this one on my mom's phone of Sam recovering from another seizure on the couch. This is seriously affecting her overall quality of life. My hopes are that with a better treatment, Sam will have happier days and no more seizures. And I'm so glad that people like you care. And thank you for researching creatine deficiencies.
I think I need a moment. Thanks, Ellie and Celeste, for sharing your lived experiences. It's not easy for those of us who work on different model systems or the like to ever fully understand or comprehend what it means to be in a family and watch your family member go through that. And it takes an immense amount of courage to deal with it every day, but then also use these types of opportunities to talk about it, because that's what it takes to raise awareness. So thanks for doing that. So I wanted to start with a brief introduction to myself. My name is Sangeetha Iyer, and I've had the privilege of serving as ACD scientific advisor for the past couple of years. Just a brief bit about my own background and my introduction to rare diseases, I suppose. So I started with my PhD in molecular pharmacology from the University of Pittsburgh. I was researching genetically engineered mouse models for different neurobehaviors. I've always had a focus on neuroscience, studied ion channels during my postdoc, mostly from the context of alcohol addiction and Alzheimer's disease, two completely different things. But starting to study Alzheimer's disease led me down the path of using model systems to look at human disorders, genetic disorders. And following that, when I transitioned to the industry, I started out with this company called Perlara, which was particularly invested in looking at rare genetic disorders and doing drug discovery for them using simple model systems. And being in this company gave me an appreciation of how difficult it is to study rare diseases, because they are so systemic, they're complex behaviors, and how critical some of these genes are to regular normal human function. Through my work at Perlara, I had the opportunity to understand all of the different gaps that are prevalent in rare diseases, many basic tools not being available, whether it is cellular systems or assays, as well as the overall lack of models. And I was fortunate to be able to work directly with patient advocacy groups during my time in this company. One of the things that I consider to be an achievement, what I'm proud to call one of my achievements, is the work that I did on a rare genetic disorder called phosphomonomutase 2 deficiency. We used simple model systems in partnership with a patient family whose mutation we modeled. We were able to find a drug that restored enzyme activity, and that drug is now in phase 3 clinical trials. As is often the case with companies that focus on really small disorders, Perlara was not successful in raising multiple rounds of funding to actually become super big, but we are grateful in that we had this opportunity to establish connections with patient advocacy groups, and the company lives on through the founder and through people who actually stayed on at the company, got out and started doing the kind of work that I do, which is really have this passion for rare disease and working directly with patient advocacy groups where you can make a difference. Following my role at Purlara, I moved into Denali Therapeutics, where I continue to do science, looking at large and small molecule discovery programs. And currently, I'm at Pfizer, where I serve as a program manager. And as part of the emerging sciences and innovations arm of Pfizer, I'm able to look at many different types of technologies that in different areas of indication. I do want to say that this background that I have has been incredibly useful in informing the way I advise ACD. However, my professional affiliations, in particular my role at Pfizer, has no representation in the work that I do with ACD. My work with them is purely for the benefit of the association, and of course self-servingly for my own interest. So at the ACD, I serve as a scientific advisor, and we have these 3 arms or frameworks for advancing towards therapies. So early on, we started out by writing a grant. We were fortunate to get this grant from CZI as part of their Rare as One foundational efforts. And through that grant, we started framing our research strategy along these different pillars. So one was to understand what are the gaps in translational therapies and how might we move towards therapies. We are fortunate that in the years that I've been affiliated with the association, we've really seen an uptick in the number of and types of therapies that are being developed for this community. 4 different types of gene therapies for CTD or SLC6A8, multiple therapies also for GAMT. We've invested in drug repurposing efforts as well with numerous academic groups. We have novel drug discovery leveraging in silico efforts that are happening at another group out of Indiana. And then finally, more recently, we're also looking into creatine mimetic delivery systems or creatine delivery system through nanoparticles directly through the brain. We've also realized that while it's important to develop therapies, we also need to have the right types of assays to prosecute them, the right types of tools, and most importantly, because we are in the area of rare genetic diseases, we need faster, quicker methods to diagnosis. So with this in mind, ACD already had GAMT newborn screening available in 2 states. More recently, in the past couple years, it was formally added to the RUSP, and now we are in the process of expanding availability of this of the newborn screening assay to multiple states, and that requires grassroots level advocacy that ACD oversees. CTD diagnosis is a gap that we have not been able to plug. There isn't a newborn screen available for CTD, but this is an area that we are looking into with experts in the field, because we do believe that faster. One, we think that CTD is one of the more prevalent CCDS out there. It's X-linked. There are likely to be a lot more undiagnosed patients that we need to learn about so that we can make the case that, hey, here's the market that you could potentially be addressing if you have the right type of therapy. And hopefully that will again, in a feed-forward cycle, lead to more therapies being developed for them. Prognostic indicators to help us understand why there are different levels of severity between CTD patients. Where are they along the spectrum? Is there such a thing as disease progression? We don't have answers to these things, and it's important that we develop the right types of tools to be able to understand this. Patient mutation characterizing assays. So CTD or SLC6A8 is a transporter protein itself, and is responsible for taking up creatine in the cell. And there's many different mutations out there. How mutations, whether they're single point mutations or truncations or nucleotide deletions, how these affect the function of the protein. This is not known. There are numerous efforts into pharmacochaperoning, and we're understanding how these patient mutations affect the function of the protein will help us understand what kind of therapies will be applicable to them. So we are investing in those types of efforts at the University of Utah and elsewhere to understand if we can develop the types of assays, make them more accessible to the patient population so as to characterize them. Last but not the least, antibodies, patient biosamples. These are critical elements of being able to do research on any rare disease. And so this is, while these look like, small tools that, we may not need to invest heavily in, we recognize that it's the gap. It's oftentimes the barrier to getting a lab to actually study the disease. And so we spend a bit of time looking into these as well and understanding how we can develop the right types of tools that will encourage labs to look at these diseases. The last pillar that we have is clinical trial readiness. In the past couple of years, we've been fortunate to be able to initiate or develop our own patient registry, which is hosted on Nord's platform. And this gives us the ability to own our patients or communities' data, to be able to conduct longitudinal surveys on it. We have an excellent registry coordinator who works with experts, clinical experts in the field, to develop surveys that will be amenable to longitudinal profiling. These are then deployed to the community on a regular basis to be able to understand progression at different ages and the like. And really to capture a snapshot of a patient's lived experience at that particular time. Patient variant reclassification. We work with several folks who are steeped in the genetics of the disease to understand how many variants are out there, how many of them are characterized as pathogenic, how many are still benign, and we know otherwise based on data collected through our registry. So what can we do to enable rapid reclassification, rapid understanding of these mutations? Similarly, along the same lines, we work with groups at the Broad in understanding and predicting, updating the numbers of prevalence based on what we know. And Heidi can touch a little bit more on that. Finally, it's critical to us that we use all of these efforts basically to understand patient population further. And one thing that I'll underscore is that while we've been fortunate that there has been a natural history study for CTD, there has not been one for GAMT. And there's this notion that GAMT being an enzyme deficiency, the fact that the diagnosis methods are available, that nutritional supplementation is a method of therapy for it. But I think, as you heard from Ellie, lived experiences are different. We believe that GAMT also is in need of better therapies. As an enzyme disorder, it stands to reason that something like that is accessible. The difficulty is because there is nutritional therapy out there and the disease is rare, there isn't a lot of impetus to actually develop therapies for it. And so I'll put a plug out there that we are looking for GAMT research projects. We are looking at efforts. We want to be able to fund efforts into enzyme or mRNA approaches to be able to replenish GAMT enzyme function. We also know that GAMT is often presents as compound heterozygous mutations. Maybe there's some amount of function associated with one allele. If there's drug repurposing approaches or any kind of pharmacochaperoning approaches to be able to restore enzyme function, that is something that we'd like to conduct more inquiry into. And I was extremely happy to hear Dr. Mustafa Sahin's presentation earlier, because we do believe that it's a natural history study into GAMT would be something that's very, very beneficial to raise more awareness about the disease. And this is something that we'd like to pursue. We've been very fortunate in that we've been steadily expanding our research network. You'll see that we have a fair amount of presence in the US as well as some in Canada. And thanks to Laura and other investigators in Europe, we are expanding our research support over there as well. We do have fellowships every year. Usually in the November to December timeframe is when we accept applications with the intent to announce funding in the month of January and February. And these are expected to be awards for early career investigators. And this is really our way of being able to expand our research network with early investigators, bringing them into the fold and giving them access to the maybe clinical KOLs, more steeped investigators, so that they can work collaboratively. In addition to this, because our fundraising efforts have grown significantly, we have grants that we apply for, as well as fundraise from our own community. We have been looking at our CTDS research centers, or CTRCs, as we like to call them, at different avenues, and the idea is to coalesce around a university that has a brain trust of investigators focused on creatine deficiencies. And we'd like to see if there are more than one, two or more investigators that we can fund in such places, so that there's more cross-pollination of efforts over there. And last but not the least, we have an annual conference. It staggers. Last year we did a virtual one. This year we'll be doing one in person. And we are fortunate that the community is ever expanding. We've had representation from patients as well as speakers from over 30 countries, and an ever increasing number of registrations, which again just speaks to the growth of the community. So this is where we stand with our research efforts, and very thankful to the opportunity afforded to me by ACD and all of the amazing researchers that I've had the opportunity to interact with, who never really turned down a request, but have always found a way to extend themselves and find something to support. So more power to us in this room, and I hope we can continue the good work.
Okay, hopefully I can add something to all of those speakers ahead of me. My name is Heidi Wallis. I'm the executive director for ACD, and I'm also the parent of Sam and Louie, who you met earlier, and Ellie. I'm going to tell you a little bit today just about who ACD is, why we're here today, and how we engage with our community, where our community is, and just kind of lay that foundation. So ACD has the mission of increasing education in our patient, family, and public community. We support early diagnosis, and we support and fund research for treatments for cerebral creatine deficiency syndromes. So for some of you maybe that are hearing lots of C's and D's and wondering what all this is, CCDS is the cerebral creatine deficiency syndrome, and CTD is the creatine transporter deficiency. And there are also two more disorders, AGAT and GAMT. And we consider ourselves a little unique because we do support all three of those diseases together, because we believe that there are so many understandings that we gain in learning about one disorder that's supportive and informative towards the other. And also we're just a tight-knit community like that. So our vision is that one day all of the creatine deficiencies will be routinely diagnosed through newborn screening. We've made a huge leap forward with GAMT. It's on the RUSP. It's being adopted in other countries outside of the US as well. The RUSP is an elite little list of disorders, and we're proud that we're part of that. And we're also very encouraged that part of screening for GAMT is screening for creatine. And so we envision that one day we will have screening for all three, and that they'll all have a treatment, and we will close down the shop, and you won't need to hear from us. So that's why we're here. Our community is all over the world, and we have some sister groups who have more localized support for the local language and the medical systems, and in close-knit support that way. But our organization also is very inclusive, and we stay in touch with all of these folks. And we welcomed 60 new families last year. We just keep seeing diagnosis increase exponentially every year, and so we're very encouraged by that. Today is actually not only the International CCDS Day here at this meeting, but it's our annual CCDS Day in our community. And every year we pick a different theme. Sometimes it's what do you want researchers to know or do, or why is it important to you? And today's theme is just simply, this is CCDS. And I think Celeste's talk and Ellie's talk, this is CCDS. We just want to tell that story. We don't want anyone to think this is no big deal, or these disorders aren't worth your time. They most certainly are. And we also want to help one another as we find out we have this disorder that we've never heard of, and how do we handle it. We have an awesome community, and people have recorded little TikTok-y kind of style recordings of their quickest tidbit of what I wish somebody told me right when my child got diagnosed. And we're compiling those all together. We're sharing them throughout the day so that we'll have a really great resource for the next 60 families that join us. So I'm going to tell you a little bit about a project that we just wrapped up yesterday. We've submitted our final report. It's a PCORI-funded patient engagement project called Parents. And during this process, we recruited a group of 25 caregivers who stayed with us the whole way through, nearly 100% of them, and all of them coming to a monthly 90-minute meeting. And we trained these folks on working with researchers, telling their story. They had one-on-one interviews, tell me all about the diagnosis, this, that, and the other. And then we put those together into presentations. And we kicked off another program called our expert panel meetings. And we had it kind of like an echo style meeting, if you're familiar with that. We had experts and then these case studies that had come from the parents so that we could engage the family stories of what is really troubling us and what do we really want to resolve with these disorders. And please, let's talk about this. Which, I think in the clinical setting, it's hard to cut to the chase. There's a lot of things to blood pressure and all that good stuff to check off the list. And we don't always get to the nuts and bolts of why is it so hard for my child to have this disorder. And while we wait for a treatment, what can I do to make their life better? So we've had 5 of those meetings now, and they've been really fantastic, really great for welcoming new clinicians and researchers into our community who have expertise in different fields that are relevant to these problems that are all kind of bubbling up and we're realizing we have in common across the diseases. And then last, we created a research paper repository for parents that have family-friendly summaries for all the creatine deficiency papers that come out, and parents go, oh, I want to know, I feel obligated to keep track of this, but it's a bit long and it's a bit much, and boil it down for me. So we've had those great outcomes, but our primary goal of this project was to come to a consensus between our families and the scientific community on what should be the outcomes measured for GAMT and CTD in any future clinical trial. Unfortunately, our AGAT population is just so very small that we weren't able to really capture that, but we did cover both GAMT and CTD in this study. And we did this, I'll just really quickly go through literature review, focus groups, registry findings. We combined all of these data points to have a list of over 1,000 potential outcomes to be measured. And through a process of community involvement, both scientific and family, through Delphi surveys, we boiled this all down to 50 outcomes. And then we brought together a group of evenly numbered parents and caregivers and healthcare providers, very, very near evenly, and had a consensus workshop. And the majority of these parents that are featured in this photo, they were part of this 2-year process. And I should have grabbed one of the very nice quotes, but we did a survey at the end, and everyone was very complimentary and impressed with our creatine deficiency community and how well informed they are. And they brought the best questions to the table regarding all of these outcomes, how to measure them. And we were told it was the best consensus meeting ever. We actually left with consensus very easily. We reached consensus on 8 outcomes, and that report of the outcomes is available on our website, and we are also working on a manuscript right now, and we'll work on publishing that. So, further supporting research and being prepared for clinical trials so that a good treatment will succeed in a trial for our families, we are here today to support the study of FNIRS as a potential non-invasive biomarker. We're very excited about this because of its non-invasiveness, because an important outcome for our kids is an improvement in their cognitive function, and that's often very difficult to assess in our community, improvements in this category. So like Michela shared, we were able to secure a grant, and we were happy to collaborate, and we're excited. We're excited to recruit families and tell them about this and share the recordings from today, and hopefully get lots of kiddos involved so we can learn more about the disease and learn more about this promising tool. And we've already done some work towards securing some travel support for the families. We're looking at having some FNIRS screening done at the symposium this summer. And Sangeetha also pointed out very well, I was going to end on GAMT has no natural history study. We're really excited that Laura and Michela were so welcoming about adding GAMT to their studies, and we hope that this will lay a little bit of a foundation for a natural history study to start understanding a little bit more about GAMT. And so with that, thank you very much. And our symposium we keep mentioning is June 29th and 30th, Salt Lake City, and we will be sending out registration information soon. And thank you for your time.
There was one question.
Yeah, there's a hand raised. If whoever that is online could please use the Q&A function to be able to answer or to ask their question.
Great. There any question, any comment one wants to make?
I'd love to ask a question, and Ellie and Celeste, I just want to thank you so much for sharing your story and your vulnerability. You know, I think it's the compassion and the lived experience like you and your children's lives that are going to create change in the future for others. So thank you. But I just kind of want to ask you, you know, in the absence of treatment, are there resources or gaps in education or resources that you feel would have been helpful for you kind of now or earlier, kind of in your experience, Ellie, that we could be working on as a
So one of the things that has helped me and my younger brothers is sib shops, and that's something that so if you don't know what sib shops is, it's this like organization that helps siblings of kids who have like rare diseases, and it helps those siblings like work through the difficulties that can bring. And I started going to a couple of those sessions like last year, and so I think if that was more prevalent, then it would be really beneficial to the younger kids.
Just in the interest of time, I think we have to move to the next talk from Irina Anselm. Irina is a neurologist here, taking care of CTD patients, and she will share with us the natural history study that we haven't done. And I would like to say it's great. Thank you so much, and thank you so much for being with us. No words. Thank you. Maybe if there is a question that we can share for later. Okay.
Well, thank you very much for inviting me to give this talk, and of course, thank you very much for ACB and for sharing the stories. It's amazing for us providers to hear the stories from our patients, because even when we get very close to the families, we still are not able to appreciate what the patients and what parents go through. So it's really, really helped us a lot. So I must say that I've been interested in creatine, in disorders of creatine metabolism and in creatine transporter deficiency for many years. And it started when I met the first patient with this condition, and it was more than 20 years ago. And after that, I've been following a couple of kids and now adults with this disorder. And I'm sure there are many more patients around who are not diagnosed. I want to share with you that it was maybe like 15 years ago. I've been already giving talks on creatine transporter deficiency, and I gave a talk to a group of developmental pediatricians. So I told them, like, when you order MRIs on your patients, like, do you the mass spectroscopy, because that's the way to diagnose. And they say, well, we don't do MRIs. And then I said, like, well, like, how do you investigate patients with developmental delays? Because it's different from what we neurologists even done 15 years ago and what we do now. And they, well, we order a microarray and testing for Fragile X. Well, this is great, but I'm sure with that, a lot of patients been missed. And so nowadays it's a little different because now whole exome sequencing and genetic testing have become available for in many situations, although still, of course, we have insurance barriers and so on. Up until now, we have insurance barriers to do a mass spectroscopy. So our radiologists sometimes do this spectroscopy for free because insurance would not approve that. So without further ado, let me just talk to you about disorders of creatine metabolism and treatments of these disorders. So there are only 3 disorders of creatine metabolism. We already heard about that. Something that I'm going to tell you is totally familiar, but I'll be just talking to you from a perspective of a neurologist who is interested in neurometabolic disorders about this condition. So one is AGAT deficiency, the second one is GAMT deficiency, and these are conditions which are autosomal recessive, meaning that parents are carriers, and with each subsequent pregnancy, there is a chance, 25% chance to have a child with this condition. And then there is creatine transporter deficiency, and this is an X-linked disorder, meaning that it affects mostly boys, males, but girls can be affected as well. That's a little bit, that's a complicated story. But as with other X-linked disorders, boys are mostly affected. So just a few words about what creatine is. It's a source of high energy because it's bound to phosphate in the form of phosphocreatine. It's a storage for energy for cells in our body. So phosphocreatine can rapidly mobilize phosphate to donate it to ADP, and that ADP can be converted to ATP. It goes on mostly inside mitochondria, and this creatine that bodybuilders use, and these bodybuilders, but that's creatine has a relatively simple chemical structure. You can see this on top. Now, creatine is synthesized in the body, but 50% of creatine we get from food. And this is just a list of products that are rich in creatine. As you can see, meat, fish, some grains, and salads are rich in creatine. But it's not enough for patients who have creatine deficiency disorders to compensate for their deficiency. So what is interesting about creatine is that creatine is produced in the organs that they need creatine, of course, and phosphocreatine, but the organs that need creatine the most, such as brain, skeletal muscles, gastrointestinal tract, and the heart, they don't produce creatine. So creatine is produced in kidneys and pancreas and in liver, and then creatine enters the bloodstream, and then it has to be delivered to this organ. So this is one of the mysteries. It's possible that there is some synthesis in the brain, but it's very, very murky area. So this is how creatine is produced, a relatively simple pathway. Two amino acids, glycine and arginine, together with the help of this enzyme AGAT, produce guanidine acetate. And then guanidine acetate is converted to creatine with this enzyme called GAMT. And so you can imagine what happens if there is a deficiency of AGAT, of GAMT, let's just talk briefly about this disorder. So conversion of arginine and glycine into guanidine acetic acid, or GAMT, is GAA, sorry, is a first step of this pathway. So AGAT deficiency is a condition that is exceptionally rare. I don't know how many patients you have in your registry. I've never met a patient with AGAT deficiency, and in the literature there are only 16 reports. Do you have any patients with AGAT?
I do have, but it's in the single digits. Yes,
Right.
very small.
Yeah, and certainly there are like 16 reports in the literature, but many patients are not reported. More than 16 patients in the world, let's put it this way. But again, this is an exceptionally rare condition which presents with, kids present with developmental delay. Ultimately, they're diagnosed with intellectual disability. But compared to other disorders of creatine metabolism, this condition is relatively mild. So most kids would have intellectual disability in mild to moderate range. They don't suffer from intractable seizures. They don't have movement disorders like patients with GAMT deficiency. They may have behavioral problems, and it's been reported that they develop muscle weakness and myopathy, but not very striking. And they can be supplemented with creatine, and they may do well. There are reports of cases that were diagnosed prenatally because the sibling had AGAT, and when this child was placed on creatine right after a child was born, ultimately the child did well. But of course, if supplementation is started later in life, that might not have such good outcome. So the second step is conversion of guanidine acetic acid, or GAA, into creatine with the help of this enzyme GAMT, and we heard about clinical presentation of these children. This probably is the most severe of these disorders, because children with this condition, they suffer from seizures quite frequently, and sometimes the seizures are intractable. They present with symptoms early on, although there are reports of some people diagnosed much, much later, like in the third decade. That doesn't matter that this person didn't have symptoms. It's just the lack of awareness, lack of possibility of make diagnosis. So these children have delays, as I said. They have behavioral issues such as hyperactivity, autism, self-injurious behavior. As I said, they have different types of seizures, and sometimes very, very difficult to control even with several anti-seizure medications. They may have movement disorder that they have because they're well, that's maybe a simplistic approach, but their basal ganglia are injured by toxic levels of guanidine acetic acid, and so they may develop chorea, which are like rapid movements, and atetosis, more slow movements, dystonia, increase of muscle tone, and ataxia imbalance. So these children can be supplemented with creatine, but they also need to be on arginine-restricted diet, not to create this toxic guanidine acidic acid. And this is from a paper. You can see like MR spectroscopy serves as a great screening tool to diagnose patients with creatine deficiency, brain creatine deficiency disorders. And this is a patient before treatment. And over here, there's several peaks on spectroscopy, myoinositol, choline, NAA, lactate, lipids. But over here, there should be a peak of creatine. And as you can see, it's extremely low, almost absent. And after supplementation with creatine, in the same patient, creatine went up. And now, last but not the least, creatine transporter deficiency. This condition is better described, better known, and there are probably more patients with this condition than with other disorders. It was described by Gaia Solomons in 2001. And after that, there were numerous reports. Patients with creatine transporter deficiency, which is due to mutation on X chromosome, and that's why males are mostly affected. The prevalence is unknown. There are different studies. Initially, we just were telling everyone that it's probably only twice less common than Fragilesse in males with intellectual disability. There are more recent studies that probably is more prevalent than we think, but again, we don't know about that. The onset of a disease is generally in early childhood with developmental delay, including gross motor delay and intellectual delay and language delay. Then children, adults ultimately develop intellectual disability. Many of these kids have behavioral problems, from looking like they have autism to having aggression, hyperactivity, self-injurious behaviors, as we heard. So that's how sometimes they're misdiagnosed with totally different conditions. And many children have seizures, but they are not that difficult. In some cases, they're difficult to control, but frequently they have just few seizures and they're easy to control. They have low muscle tone. They frequently have gastrointestinal symptoms like dysmotility. They may have eye movement problems. And what's been described of various facial dysmorphic features. I must say that among patients, I've seen only one maybe had dysmorphic features, a child who had a large deletion, was severely affected. He had large ears, deep sunken eyes, but all other kids, they look totally normal, totally normal. They look like their parents. Cardiac involvement is interesting because we had two patients with heart involvement. One had prolonged interval, was followed by cardiology. Even before he came to us, he was seen by cardiology. He was on medication for that, and then ultimately it resolved. He's been off medication for years now, doing very well. The other child had PVC, premature ventricular contraction, and also ultimately he did well. So this is one of the mysteries about creatine transporter deficiency, and I heard it from other providers that some kids would have heart problems that later get better. So the third of patients have de novo mutation. Of course, this is good news for families who have several children, that it's probably just a child has this creatine transporter deficiency and other children are unaffected. I follow several families like that, but of course, mothers could be curious and they have to be counseled about it. And, there are no clear genotype-phenotype correlation. Just looking at some reports, it is possible that missense mutation, they do not produce such severe phenotype as deletions, but it's not fully clear. So I put it down that there is some researchers found high creatine levels in cerebrospinal fluid, which is very interesting. It only means that these patients, they cannot move creatine from spinal fluid into neurons. So it is possible that there is some synthesis of creatine inside the brain, but of course that has to be investigated. And then heterozygous females. I've seen two girls with where it was felt that their delays are due to them having this creatine transporter deficiency. In one of them, I follow several kids whose mothers have that. So with girls, it's a little tricky because they could be just curious, and if they have delay, it's not totally clear in some cases that really the delays because they have this mutation, right? They may be delayed for other reasons. So that always requires investigation. And of course, if you do MRI and MR spectroscopy and the girl does not have a creatine peak on spectroscopy, so it would be more convinced that that's the story. But there's no direct correlation between spectroscopy in girls and their disabilities. It is a murky area, and also these studies of us to X chromosome also do not give a direct answer to that. So as far as treatment of creatine transporter deficiency, there were multiple attempts to treat these kids, and they were placed on creatine, monohydrate, placed on arginine and glycine, thinking that arginine and glycine will get into the brain using their own transporters, and there will be synthesis of creatine over there. These attempts were not extremely successful. Some studies, but they're very, very, these studies, they only have few patients in these trials. Some report maybe some slowing down of the disease, maybe effective in girls, but not as much in boys. So this is just a list of studies. There's like a review of all the studies that reported treatment of patients with creatine transporter deficiency, and most of them just demonstrated that there was no significant improvement, that there was a possible benefit in one report. So this is one of our patients. This is spectroscopy before he was treated with creatine, arginine, and glycine, and you cannot, like, creatine should be here, you cannot really see it, and this is years after, exactly the same. So unfortunately, it did not work for this boy, although he's doing much better clinically, but I cannot attribute it totally to the treatments that we do. Now, also, while I said that nowadays genetic studies is like the mainstay of making the diagnosis, in the past we've been sending blood and urine for urine acid and for creatine ratio, just to have an idea whether a child may have creatine transporter or GAMT deficiency. And this is just an illustration of what we might anticipate from metabolites. So it's sort of clear, like with AGAT deficiency, guanidina acid is not produced. With GAMT deficiencies, the opposite is produced, but the creatine will be low in both cases. And with creatine transporter deficiency, we were looking always for elevated creatine ratio, because the creatinine is a product of phosphocreatine, and these patients don't produce enough creatine, decreased reabsorption of creatine by kidneys. But of course, this is a good way to look at that, and genetic testing is a must. So I would like to share with you a story of one of my patient is now 28-year-old man, and I've been following him for many years. Initially, he was followed by other providers, so he had a diagnosis about it. And he first came to neurology at 12 months for gross motor delay. He also had failure with 5, GI dysmotility. He's the one who had both prolonged QTC and ventricular apathy. Had brain MRI 2 years, and it's totally normal. So was followed, and then ultimately he, at age 10 years, got MRI with a mass prospective, and again, colon peak and a peak, no creatine. This is how diagnosis was made. He was found to have a mutation in this gene, and since then I've been following him. He developed behavioral problems over the years, mostly hyperactivity and some aggression. Then it got better. He is on medications for that, and his behaviors are great right now, although he does have some anxieties, as I said. His heart problems resolved, his gastrointestinal problems resolved. He had several seizures on one medication, very easy to control. His parents gave me permission to share his photo. Actually, double-checked yesterday, thought this is perfectly fine, just to demonstrate how adults with this condition look. You may see that he does have some wasting of his muscles. He's very thin, but he's not weak. And this is another mystery, right? Why aren't these people weak, right? They're strong. Yeah. And then another patient of ours, and this is an illustration of another misdiagnosis. This kid, when I met him, he was 3 years old. He had significant hypertonia since birth, severe delay, and he had elevated blood lactate. So parents took him to a special center where patients with suspected mitochondrial disorders were evaluated. He had muscle biopsy, was diagnosed with mitochondrial disorder. Then he came to us. This is his mass spectroscopy. Again, no creatine peak. And so he ultimately was diagnosed with Creatine Transporter Deficiency. So in conclusion, I want to say that some of these conditions are treatable. Of course, we're looking for more therapies, for gene therapies and so on, but patients with AGA deficiency may benefit, patients with GAMT deficiency may benefit from diet, from treatment, and of course also it's necessary to make diagnosis for genetic counseling to help families with family planning and so on. So every child with unexplainable intellectual disability has to be tested for disorders of creatine metabolism, and spectroscopy has to be added to MRI. It's about 10 minutes, but it's always a barrier with insurances. Hopefully, will not continue to be an issue. And prevention of brain damage is the final goal of family diagnosis. So I want to thank everyone for listening, and thank you again for organizing, for your participation.
Question. When is the onset of seizures? Do you see a different time of onset, or in general, early life?
Well, I think that it's a bit unpredictable, and not every child with CTD, I can talk only for that. I don't have patients with GAMT deficiency. I know someone in epilepsy has, but with CTD, I have a patient who does not have seizures. This patient who is 28, he started having seizures literally a few years ago. So it all depends. But the patient who was initially diagnosed with mitochondrial disorder unfortunately passed away because he was severely affected. He had intractable seizures from early on. So it's totally
I have a question. Thank you for speaking. I also have a son with CTD. He's 4.5, and I'm just here opportunistically. I'm in contact with Heidi, so really happy to be here listening to this. So my son's experienced a very severe hypoglycemic event when he was 3.5, and I'm just curious if you have seen that in CTD. His blood glucose was 15 by the time he got to the ED, and very scary, obviously, because we don't know how he survived that. But he's recovered well within, saline infusion. But that's something that I've kind of brought up because that with rare disease, obviously, you never know. There's not a rule book. Have you seen that? Have you heard of that? Yeah.
How to explain it.
Yeah, and he was tested for other like GSD1A and other type conditions. He was, growth hormone, all of that was normal for him. But
that was the only one episode that
yeah, and it was after just like a stomach bug and not eating well, and I'm assuming because he has all of the hypertonia and all those, he wasn't up to, there was no uptake, and maybe it was like the perfect storm for him. But I've been it's scary. We make sure he's eating, and we supplement now with cornstarch if he's not, kind of like GSD1A patients. But it's I just didn't know if that was something that was out there in the.
I didn't come, not definitely not in our patients, but I not see that.
Okay. And then my second question was, did you know anything about betaine? I know that's kind of a newer supplement that my son started a few months ago. And I think that, I don't know if anyone's following that to see if there's any links with that.
We've been a part of that. I don't know about.
Okay.
Don't have such childhood experience.
Okay.
Thank you so much. And now we are moving with our first speaker to Zoom.
I think we are muting ourselves. Are we muting ourselves? Yes. So I'll let you intro her first. Okay. First, I introduce Judith Miller. She's a psychologist at CHOP in Philadelphia, and she had been leading the VIGILAN observational study for CTD, and we are very lucky to have her here with us. We wish she was here in person, but she's here. She's here, and that's the most important. That's the good things from COVID that we've learned, and we can do even this way, and it's good. So thank you. The stage is yours, Judith, and please start.
All right, welcome. I'm very happy to be here and share this with you. And I see in the list of people here attending, I see the name Alexandra Bruchet, who is one of the first people I met in this endeavor. She was with Lumos Pharma and helped get this whole thing started. So it's fun to see her name, and I hope she's doing well. Okay, I am gonna try to share this, but if somebody would tell me if this looks right. Is this the right screen for you guys?
It's on the version where we see your notes.
Okay.
See your...
All right, I will swap. Okay, is that better? Okay. All right. Okay, and I will try to watch the time and see how we can do. Okay, so I'm pleased to present the final results of the VIGILAN observational study. And it's not all of the results, but we have the final data set. And so this is some of the high level things, but we can talk about in a few minutes. And I just wanted to thank all the families and the study sites. So here's a list of the study sites that were involved, and some of the, most of the PIs and psychologists and study staff. So we're grateful to everyone's help. This was a big endeavor. Here's some potential conflicts of interest. I'll let you guys just look at that for a minute. This study was sponsored by Ultragenyx ultimately, but it started, like I said, with Lumos Pharma. So, and several of us do provide some consultation to Ultragenyx or are employed. I myself am employed at Children's Hospital Philadelphia. All right, we had a beautiful background on CTD. So as you know, it's an X-linked recessive disorder. The typical symptoms include intellectual disability, autism, significant delays in speech and language development that most of the time persist. into adulthood, and a lot of behavioral problems, seizures, motor delays, hypotonia, and hypertrophy. It was really, really touching to hear the family stories earlier, and really resonated with, I think Levi is a good example of some of the challenges and characteristics and beauty of CTD. All right, the current standard of care, you got a little taste of some of the supplements that can be used. Otherwise, the focus is usually on skill development. So it's on physical therapy, occupational therapy, and behavior therapy, and medicines to control seizures. And seizures are generally controllable for the most part in CTD, but there aren't currently any medications, but there are some things in development. We hope they're successful. So VIGILAN is the name of the study, and we enrolled 50 males with confirmed CTD diagnoses, and then we followed them for up to 48 months. So we took, I think, 6 years to from beginning to end for data collection, and we didn't get 48 months on everybody. We stopped a little bit short because we were so close to the end, but we have a lot of data over a long period of time. Our caregivers completed surveys every 2 months, and we saw participants in person every 6 months with some interruption during the pandemic. But that was the general study design. And our goal was really to understand the course over time and contribute a longitudinal study, and then also to contribute to how to develop therapeutic programs. So identifying potential endpoints, potential measures that could be relevant and feasible to collect in this population, and then notice if there's important things that happen over time naturally to see if that might inform how you plan and design an intervention trial. So our little bit of our demographics, we had 50 males, and we focused just on males. It's hard to imagine. I hear a lot about girls with CTD now, but 8-9 years ago when this was being designed, girls with CTD were just really like unicorns. So there was very little known about them. And the little bit we did know, we understood that they were very different from each other and different from males. So this study focused on males. Most of the folks who participated started out when they were 12 or younger at baseline. So our age range was 1.5 to about 25, but most of them are in that under 12 age range. And then just for kind of speaking to the family experience, it took about an average of 3 years from the first time the family brought their child to a professional for an evaluation to the time of ultimately getting the diagnosis. As you can see from the figure on the right, we know from hindsight that the first symptom was often before the first birthday, but that's not when parents take their child for an evaluation. You usually have to have a period of kind of wait and see what happens. In our sample, the first evaluation was averaging at about age 21 months, but then the diagnosis happens closer to 4 or 5 years old. And that's something we can hopefully improve. We would need to improve that in order to have good intervention. And having an effective intervention would also motivate procedures to get insurance coverage and other things to screen and diagnose early. So they are kind of related to each other. Neurologically, seizures were the most common reported symptom in our sample, but there's a host of other things that occur. Not everyone has aggressive behavior. Not everyone has attention problems. Not everyone has autism, but a fair number do. And they really contribute to both the current presentation and also how you would plan a intervention study. Because if you might have an intervention that works on one aspect of the child's struggles, but might not hit all of them. So it's important to sort of characterize your sample well so you have a sense of what may be contributing to the child's current level of ability. We looked at GI things across time, and there's a lot of difficulty with toileting. So these things are labeled incontinence, but it's probably more accurate to recognize that a lot of our sample really struggles with toilet training, and that's a challenge for many years, and for many people into adulthood. So toileting is a big challenge, but then there are other issues. There's a lot of early vomiting. You've heard that a lot of GI things, or in some of the patients we've heard about already today, sometimes the GI issues resolve, which is true, and that's great. But there are a lot of them if you look at how many there are across the lifespan in the whole patient population. In our sample, this is kind of an image of language levels. The most important thing to look at here is the total column, because I failed to put the number of kids in each group. Most of our participants are 12 and under. So there's not that many 12 to 18-year-olds, but this is a proportion. So put your eyes on the total at the end, and notice that the majority of kids, of adults, individuals with CTD have limited language. There are some that are speaking in sentences, but that is not necessarily fluid and complex sentences. So most folks are pretty limited. Okay, I'm just gonna focus on 3 areas: cognitive development, adaptive skills or self-help skills, and behavior. And the reason to focus on those is it's a measure of your development, and it's what you would hope changes with a real intervention. You know, we know from kids with other creatine deficiency syndromes that if they can get the right supplementation early on, you can see their development is really terrific, and you know, sometimes even just unaffected. That's the goal, right? That's what we're going for. So looking at kids' cognitive development and adaptive skills and behavior is a really important way to measure that. One of the challenges we have, though, is that IQ tests are not designed to show progress over time. And Audrey, I think, is going to talk more about that in a few minutes. So I won't go into too much detail. But I really especially like for the parents in the audience, the parents and the basic scientists, to understand the limitations of some of our neurodevelopmental measures. So this figure shows, has 3 panels. These are all measures from our IQ and cognitive development measures. And what's important to notice here is not the fluctuations in the scores. Each of these little lines with the dots is one patient. What I want you to notice is just that the clustering, most of the scores are in the lower half of the table. So most of the participants are at least moderately intellectually disabled. There are a few that are only mildly intellectually disabled, but most are moderate to severe. And they stay in that range. They stayed in that range during the course of our study. This graph is the same idea, but with adaptive skills. So when we ask parents, you know, what really matters to you in terms of what would make a meaningful difference in your child's development, most of the time it's about skill development. Like, I want them to talk. I want them to be able to do things for themselves. I want them to get toilet trained. I want them to have fun going out in public. I want them to be able to participate. Those are a lot of things related to self-help skills. I want them to help out around the house. I want them to participate in cooking. So we use a measure called the Vineland Adaptive Behavior Scales. It's very widely used. And one nice thing about the Vineland is that there are some different things you can do with it that you can't do with an IQ test. I mentioned that an IQ test is not really designed to measure change over time, but the Vineland has some statistical properties that lets you measure change over time. And that's great for a disorder that's rare and for a disorder that has a pretty significant impact, because if you are starting out from a pretty impaired level, like if you're moderately intellectually disabled, you want to be able to detect any kind of meaningful change. You don't want to set that child up that not only does he have to change relative to himself, but he has to change relative to all the other kids in order for his score to move relative to all the other kids. You just want him to be able to measure him against himself. And if you can tell that he made growth that was more than just expected from time passing, then you've got some evidence that your intervention was effective. So that's what we're trying to do with the Vineland. So this panel shows us the 9 different sub areas of the Vineland. So we've got receptive language, expressive language, written language, personal care skills, domestic or around the house kind of self-help skills, community self-help skills, like crossing the street, being able to recognize signs, that kind of thing. And then the third row is socialization things. So interpersonal relationships, playtime, and coping skills. What you can see from these scores, what you can see here is the red dashes. Statistically, those red dash lines are what we consider an average ability, right? So that's the normative data. So our participants are, for the most part, they're below average, and they're kind of scattered around the range here. But if you see, there's a lot of measures where there's a lot of people at what we call the floor, right? So if you look at the bottom of each of those boxes, you see this long line of dots. That means they're at what we call the statistical floor, and the test doesn't go low enough to capture their true abilities right now. That happens when you're trying to make a test that is designed for the entire population. There aren't enough, as you get to more and more ends of the extreme in terms of either those who are like highly gifted or those who are significantly impaired, there's just so few kids that it's hard to really get items that really measure those ends. So that's a problem with a lot of standardized tests. And that's a problem with IQ tests and with some of the scores on the Vineland. But the Vineland has this other scoring option called a growth scale value. That's one name for it. When it's used, when that term is described generically, it's called a person ability score. And it reflects the idea that you're measuring that the ability of that single person. It's not relative to the whole population. So this growth scale value or person ability score is what is going to be able to let us measure a person against themselves from the past. So my 3-year-old self can be compared to my 2.5-year-old self. And there are statistics that let me know, did my growth exceed what you might have expected just from time passing? Everybody learns something new as you go through time. Our kids with CTD learn at a slower rate than other kids, but they do still learn. So we want to capture that. And the growth scale value really lets us do that. So what you can see here is you can see there's not that many scores that are on the floor anymore. We're up off the floor, which is great. So in the receptive and expressive panels, you can see really nobody's at the floor. In the written, a lot of kids are at the floor. A lot of our kids are not writing very well yet. So from this, we could say, receptive and expressive language might be good domains to study in an intervention trial. Written language, not so much, because even with growth scale values, we still got a lot of kids on the floor. So what we've done for VIGILAN is we looked at all of these, and we are characterizing how kids change over time. And then we're also noticing which ones of these are going to be really helpful and measurable in an intervention trial. I forgot to mention the red dot here, the red dots, those are also, just like the straight line was the average score in the slide before, this is the average score. So this is the average trajectory that you would expect in that area over time for all the kids that take the Vineland. So you can see our kids are still below that, but they're moving and they're making some growth and it's noticeable and they're not all on the floor. Okay, and then the other thing that we can talk about briefly is behavior. So we used the aberrant behavior checklist. When we designed this study, we knew that a lot of kids with CTD have challenging behaviors, and the aberrant behavior checklist has been used in some pharmaceutical trials in the past. So it made really good sense to say, let's see how this works in our population. And it's been helpful to give because it shows us that not everyone with CTD has significant behavior problems. So as you can see, the two lines on top, the gold one and the blue one, they are demonstrating they're showing the results for the irritability and the hyperactivity subscales. So we do see a lot of kids who have challenges in that area, but it's not universal. And so it would not be the best measure for like the primary outcome of an intervention. If everyone with CTD had really elevated behavior problems, then that might be a good marker. But when only some do, you don't want to have that as your primary outcome because you don't have enough room. People need to have room to improve. And if you're already not struggling with that, it's not really a good outcome measure. Okay, so just to bring it back to closure. So what we found over time was that our participants, the symptoms occurred early in life, but there's often a long time to diagnosis. And like I mentioned before, that's an area that is really worth investigating more to see how to do better and get earlier identification. Our participants with CTD had a range of neurologic and GI symptoms, and their difficulties with language and cognitive ability generally persisted. While they do grow and change and gain some skills, it's modest. And so there's what's helpful to know about that is it's really nice to confirm that kids with CTD do learn new skills and they are growing and they are developing. And if they're growing and developing, that means if we can get an intervention that is helpful, we should see that growth and development accelerate because growth and development hasn't stopped. It's still happening. So the idea is an intervention would help enhance that and make it even more promising over time with even greater skill development. Okay, and then of course we would want a therapeutic intervention to start at a young age to really try to help improve outcome as much as possible. Okay, and thank you to the families who contributed and participated. All right. I'm happy to answer any questions.
I'm wondering, can you hear me at the back? Can you hear me? I'm just yes, in your study, when you're looking at different age, do you see a age-dependent changes? For example, older population, do they have more regression or maybe the progressing not as well as those younger ones? Do you see that difference?
Great question. We do. We see that, you know, the younger kids, there's more room for them to develop. So we do see their trajectories. Everybody is making modest gains, but yes, if you're younger, you can see more development. But the older kids don't stop developing. There's some fine-grained analyses we're doing about that we're putting into a publication. So age does matter, but it matters in degree, not necessarily that development doesn't stop.
And then we have a question from the online group. So Emily asks, Dr. Miller, you mentioned that not all participants show behavioral issues. We have heard in our community that behaviors get worse once they hit puberty. Since most of your participants were less than 12, did your data reflect that increased behavioral issue?
That is a great question, and I definitely hear that a lot. And we did have some participants, even at our site, who hit puberty during the study, and it was like a switch went off. So it does. I mean, so I'm not comfortable saying this. It's universal, but it's very common experience. And so yeah, it's a very good point. Like that doesn't. So we didn't get all those kids. But it also is a good point. Like you still wouldn't want that to be your primary, because there's an interaction between puberty and CTD that's happening. I mean, everybody's a little irritable. Everybody's a lot irritable when they're teenagers, right? Like that's just a thing. But so you wouldn't want to confound puberty with CTD. You still would probably want to look at something that is not related so much to puberty as an outcome measure. You still would need to treat that. There are a lot of kids with CTD who then, use behavioral meds to help control their aggression and other kinds of things when they're hitting puberty. And then we also, if it's any potential for optimism, we do then hear that a lot of those behavior challenges go away when puberty's over. So you only have to wait till they're like 25.
We have one more question.
Yeah.
Hi, Dr. Miller. This is Sangeetha. I had a question about the hyperactivity that you see in CTD. I was wondering if you could comment on whether that hyperactivity is different from what you see in other autism spectrum disorders, if there is some sort of comparison that you can make. And then the second really maybe related question is there some sort of correlation between the hyperactivity and irritability, or not really?
There is an association or a correlation. So we don't know if one is causing the other, but yes, they do seem to kind of go together in the same kids. There's a group that has both. Then there's a group that has neither. So there is some separation there. As for the quality of the hyperactivity, so hyperactivity is tricky. When you have an intellectual disability, you need to be careful that you're not. If you can't cognitively participate in like a board game or other things that require conceptual understanding that you don't have, you might be wandering from thing to thing because you're trying to find something that is fun for you to do and that you understand how to do. So as a clinician, you're always trying to figure out, like, is this really hyperactivity? Like there's a lot of extra energy and movement, and we're kind of hyperactive even compared to what you would expect for someone with this level of intellectual ability. And that's what we struggle with in autism too, is are we truly hyperactive from a physiological standpoint, or are we trying to find something that is going to, capture our interest? Audrey can comment, but I think in the realm of DD, that hyperactivity, there's a wide range of ways that can present. I think probably the main difference is in CTD with or without autism, you have a significant intellectual impairment. In autism, you may or may not have an intellectual impairment, and so there is a little different quality to the hyperactivity that you can see, but it's probably very similar to other folks with intellectual disability who have the same sort of motor skills. These kids, even though they're thin, they're strong, and they are very, they're ambulatory for the most part.
Okay, just in interest of time, we would like to say thank you to Judith. And then now we would like to switch to Aurore Curie. She's from France, from the Hospices Civils De Lyon, and she will be talking about Creatine Transporter Deficiency and another prospective study to define new outcome measures for the disorders. Thank you, Aurore.
Can you hear me? Can you see my screen?
Yes, you can hear you.
Okay, perfect. So first, I would like to thank the organizer to give me here the opportunity to talk a little bit about this study, which is called CREAT criteria. that is still happening in France. So it's a prospective study in creatine transporter deficiency. And the goal of it is to determine the most relevant outcome measures. Of course, given everything that was said before, just during the other talks, I suppressed some of my slides because I'm sure that you know everything about CTD now. So I will just go straight to the point. So every one of you is totally convinced that it is necessary to identify objective, reliable, and sensitive outcome measures. And the problem is that we need to test a broad range of abilities, as we do not know yet what kind of domain can be improved by a future treatment. And of course, we hope that the treatment will work, but it's difficult to predict what area will be improved. So what is also very important is to quantify score defect, meaning that given the presentation, as Judith just told you, and the presentation before, given the fact that they have intellectual disability, the core defect of these patients is really reasoning impairment and inhibition problem too. And also, it needs to be correlated to the quality of life, and we need to be able to measure a true functional improvement. So with that, we designed this study, which is called CREAT criteria, as you can see here. So the objectives of this study are multiple, as you can see. So the first one is to determine relevant endpoints to be used in future clinical trial involving CTD population in terms of feasibility. And we would like to know if we can assess these patients despite their cognitive deficit. So we would like also to assess the feasibility of single case experimental design. And we try to test if it was possible to assess, multiple endpoints at home using, for example, tablets. And as I will show you an example later. We did want to see if it was feasible to use MRI to better have a better idea about of course, the spectroscopy peak, but not only, also looking at the morphometric analysis and the functional MRI. And of course, we would like to describe the neuropsychological profile of CTD patients compared to sex and chronological age match controls first, and to mental and sex age match controls. And we would like to see if the new endpoints that we developed were able to capture the cognitive abilities of CTD patients. In addition to that, we had 3 ancillary studies. One was about the neuroimaging profile. So we did structural and functional MRI, DTI, and spectroscopy. So it was a full neuroimaging study. We also performed a cardiac assessment because we did want to see, to compare what Dr. Levin found in US patients to see what was the case with French patients. And also we created a collection of biological samples because we did want to have access to, to make it possible to researchers to have access to genomic and clinical data with blood, urine samples, and fibroblasts. So this is at the Hospices Civils De Lyon. So we will include 24 patients. So the age is a little bit older than what Judith just told you, because we did decide at first that we will include patients aged from 5 to 35 because we did want to be able to test the cognitive endpoint that we developed. And we saw that maybe below 5 years old, when you have intellectual disability, it's sometimes difficult to. We are planning to do an additional study, but for now we did start with that. So each CTD patient is matched to a sex and chronological age match controls and to a sex and age match control. So basically, you have 24 chronological age match controls, age 5 to 35, and you have 25 mental age match controls, age 3 to 8. And additionally, we did want to finish our validation study for the different endpoints. We already validated it on 100 participants, but we did add 80 more typically developed children. So here, the main study was really to compare the profile of CTD patients to the controls. And the three ancillary studies, as I told you. So I will not have enough time to show you everything, but I will really do my best to be there in June, and I hope to have final results to show you in June. So we also include 9 patients among the 24th accepted to participate to this longitudinal study. So it was very interesting because there were, the first visit happened in Lyon on site, and then every 2 weeks they were tested using a remote session like what we are doing now, Zoom session, and the parents were helping the child to use the tablets. So it was recorded online, and we could check if everything was going well. So the idea was really to see first, is it possible to test these patients at home? And as you will see, the answer is really yes. And the second thing was, is there any difference when you test them at home versus on-site? So we added 2, so in total it was 3 on-site visits, visit 3 and visit 7, and the first one, of course, and all the others were performed online. So the first endpoints that we did look at were clinical endpoints. We also looked at a lot of parental questionnaires. We used also the Vineland, as Judy just showed you, the EBC, a lot of different questionnaires that we used. Also quality of life questionnaires and care burden inventories also for the impact of the disease on the parents, as it was already mentioned before. We also did a lot of different cognitive. We did try, because the idea was to test different cognitive way to assess patients. So I will show you some results about that. We also had language, motor assessments, social assessments with ADOS performed on each patient, because we also did want to really look at how we could, measure and improve the autism, at least the autistic feature that they could have, and the ancillaries endpoint that I already mentioned. So here I am going to present to you preliminary results. So up to now, we started the study at the end of March 2023, and we have included 20 patients. So the longitudinal study is finished. So 20 male CTD patients with a pathogenic SLC6A8 variant were included, and 9 of them participated in the longitudinal study. So just to compare with what you have just heard about developmental trajectory, very nicely presented by Judith, you can see that here we have slightly older patients. The youngest is 6.7 years old, and the oldest is 25, with a mean age of 16. The age at first symptoms is around 12 months. It can fluctuate between 2 to 30 months. And the age at diagnosis is slightly older than what was described by Judith, but it makes sense as the patients were slightly older, and we showed that the younger the child is, the younger also the diagnosis is made, just because the disease is not known for a very long time. So regarding the clinical endpoints, we did use an exhaustive clinical interview. We checked the family history. We also tried to have a very precise developmental trajectory. Parents were really wonderful. They did check. They found picture, photos, films, movies. They checked. They called us back. I mean, it was impressive work. And we also spent a lot of time regarding the characterization of epilepsy, not only onset, but also the treatment that were used, the hospitalization, the seizures types, and also the frequency of seizures, the duration, the pharmacoresistance, and we performed a centralized analysis of EEG. We also performed physical examination for all patients, including a thorough neurological exam, including walking and balance. And we defined with the parents, as you can see, parents were really very much involved in this study. So we defined with each parents for each child a specific symptom that basically the parents would like to be improved by the treatment, but we needed also to have something that can be really measured in a daily basis. So it has to be something that does not happen just once in a while, but is really observable, can be really assessed on a daily basis. And on these symptoms, we ask them to rate this symptom. 0 was when you had no problem, and 100 was the maximum of the problem. We also perform actimetry analysis. At first, and Judith, when she visited, remember that we were a little bit afraid about, is it possible, not? But it did go very well. We had only a few patients that could not perform it. So as you can see here, it's like it has to be, it looks like a watch, and you have to warn on the wrist of the non-dominant arm. And as you can see here, it's very interesting because we were able to quantify the latency of sleep, how much time they need to fall asleep. So this is a result for all the patients that performed actimetry. We also compute the total sleep type, but also the mean wake after sleep onset and the mean number of awakening, which is sometimes really difficult for the families. We also looked during the day on the level of activity, and we were able, I don't know if you can really see here, but basically we were able to define the amount of time that they are sedentary, the amount of time they are having moderate activity, vigorous and very vigorous activity. And we also computed for each patient the average steps per day they were making. So basically you can see here 12,200 steps per day. I don't know how many steps you are doing per day, but it's interesting to compare. And of course, for all this, we also have LC controls. So we also did a 6-minute walk test, and we checked if it was feasible or not to do MRI without anesthesia using a MOG scanner. So here you can see the different pictures of it, and it did go very well because we had a very high rate of success for performing MRI in CTD patients. So we did 3T1 high resolution acquisition, and it was interesting to know that the vermis, the cerebellum, we noticed some of them had slight atrophia. And we also did like usual sequence to have a good idea about the morphometry of the brain, so T2 flare. We did spectroscopy, DTI in a resting state. So regarding the spectroscopy, we did long echo time, and you can see here the result, but I will go fast because you have already seen that several times, so I don't want to bother you. But basically here you can see the very low and decreased peak of creatine in this patient. And here, because we have age-match healthy controls, you can see the difference for an age-match healthy control. So basically it's really comparable. We did also that for the short echo. Basically, it's technical, but it allows you to measure a little bit better the level of the level of the peak. And what was interesting is that we were able to modelize the activity. So basically, you have the spectroscopy here, but we did not usually, and you have seen that many times. Usually, we just look at it at the peak, and clinicians know that by heart. We just say, okay, it's very decreased, severely decreased, or not. But here we were able to quantify the peak. And what was interesting is that, so here just to explain, so you have in dark, in black, you have the actual signal, and here you have the residual noise. Here you have the macromolecule signal, which is always difficult in spectroscopy to modelize. And here in green, you can see that it is a fit of the modelization of the spectroscopy, which is really very good. So we are very happy with the results. And of course, CTD patients had decreased creatine quantification. That's not a mystery. But what was interesting is it seems like to be correlated to the IQ result using the lighter, which is interesting. So regarding the cognitive assessment, we used the lighter scale, and we were very happy about it because we were able, up to now, out of the first 20 patients, and the last 2 patients have just been included this week, so it's very, very fresh results. We were able to assess lighter scale with for 19 out of 20 patients, and the mean non-verbal IQ was 56. So for us, it was like I mean, we were very happy about that because, I mean, we do not have in France, in Europe, I don't know, Laura, you might answer that, but at least in France, we do not have WASI, which is a short version of the Wechsler scale. And the lighter scale is very interesting because it's non-verbal and it allows yourself to go lower than you can do with a Wechsler scale, because with a Wechsler scale, you cannot go lower than 45, 40, depending on the age of the patients. But here you can go as low as 30, which is very interesting to assess the cognitive intellectual ability of the patients. We also used CPMBF. So what is interesting is that the patient can manipulate it. And of course, the first one is not too complicated, but it increased, the difficulty increased. And a lot of patients were able to perform this test. Of course, the results were kind of low because we got a mental age of 4.5 years old. But it's interesting to be able to assess that. I will go I mean, I don't think it's just to show you, because we also did use the Vineland scale and we found similar result to what Judith just explained to you. So the different domain, you can see that they were really very impaired, and the V scale that she showed you already. So basically a little bit better in receptive, in domestic, and in gross motor than in fine motor skills. So I will go straight to what we really developed in the lab. So we developed 4 simple reasoning tasks. And what is interesting is that each task is with an increasing level of difficulty. So you can see we have the match to sample task, categorization task, matrices task. I will show you, of course, pictures in a few minutes, seconds. And the last one is implicit rules learning task. What is interesting is that we really have a level, 4 levels of increasing difficulty. For example, the first level was really performed in 19 out of 20 CTD patients. So 95% were able to perform it. The categorization task was really very well performed too. In at least 85%. It is possible that one additional patient can do it when he will come back for the MRI. The matrices were a little bit more difficult. Only 70% were able to perform it, and the last one was even more difficult. So here it goes. So the first level, match to sample task, we just used a familiarization just to be sure that they could understand that what we were trying to do is to find what character is the same as the one above. So basically, if you click on the right character, then it turns on itself, so giving an immediate reward to the patients. So if we can do that with Disney character, then we go for the real test. And we had 2 different conditions: the matching condition, where it's the same, you have to find what is similar to the one above. But here the wrong answer, the false response, is different from the target. And the inhibition condition, where it's a little bit more tricky because it looks like the false response looks like the target. So you have to inhibit the fact that it looks like the target. So here it goes on the tablet. And I don't know if there are some parents from the study here, but they know the task very well because I did it with a child at home. So here we already validated the results on more than 100 participants, and we showed that there was a significant inhibition effect and group effect on the reaction time, which is nice. And of course, there is a correlation with the age of the children, which is also makes sense. And we also did an error rate analysis, sorry, and we found that there was a significant inhibition and a significant group effect. What is really interesting is that you can see here that it's really the youngest children, 3 to 4 years old, that are really impaired by the inhibition. So here are the results for CTD patients. And you can see here that we have the impression that they were really impaired by the inhibition, more than, of course, the chronological age match controls did not do any mistakes, which is good for them, I would say, for this task. And of course, it would be very interesting to have the mental age match controls that I do not have yet, but I will try to show you in June if it's possible. The categorization tasks now, so we had 2 conditions, the simple condition, where we had to, I mean, it's the same principle, but it's not exactly the same figure that you have to match. It's really to put together here the trousers with the shirt because it belongs to the same category. But the beauty of it is that you do not need to have the word to say it's a clause. You do not need to say it, but you just need to click on the right answer. And the participant did understand that quite well. We had a more difficult condition where the false response was closer to the target, making it more difficult to understand. So here it is. So you can see, you can try if you would have chosen what the participant chose. Just I know I have to go to keep going, but here it is. So here are the results on 100 LC controls. And you can see that we also have a difficulty effect on reaction time and a very strong difficulty effect on error rate. And it's really interesting to note that all the groups made more mistakes for the more difficult condition, including the adults. We did design 2 versions of the task, version A, version B, because we did want to, as I showed you, to do test-retest and longitudinal study to see if it was feasible to use different images just to see if it was reproducible, and it did go very well. So we have a very good test-retest reliability. And here you can find the results on the first 14 CTD patients. And again, we had a high impact on the difficulty level. Then we did design another task that, because we did want really to target the reasoning, and it is inspired by the progressive Ravens matrices, but really more simple and appropriate to ID patients. So we had 3 levels of matrix complexity. The first one was where the elements from the matrix were all the same, so it was kind of easy to find the right answer. Here it got a little bit more difficult because you have to understand that the shape is changing in order to find the right answer, so one relation matrix. And then you have to understand that you have to take into account the fact that the shape is changing and the size of the elements is changing. So to find the right answer, you have to combine both relationships that are involved. We also did add 2 different types of false response. The first one was neutral false response, and the other one was a to be inhibited false response, meaning that the false response, the one that you should not select, was already present in the matrix, and it made it harder to decide the right answer. So we did a mathematical modelization of the developmental trajectory on reaction time and error rate on more than 100 LC controls. So basically you have 5 different conditions. So identical, one relationship with neutral false response, one relationship with to be inhibited false response, 2 relationship with neutral false response, and 2 relationship with to be inhibited false response. So what is very interesting, this is really the first time I'm showing these results. So regarding the CTD patients, what is very interesting is that they are making more mistakes for the one relationship with to be inhibited condition, meaning that they are making more mistakes for something which is more simpler, than something more difficult to relationship with neutral false response. So it's interesting to see that there are, abilities that are there, but we have to have the right test in order to assess them in the right way. So we are happy with this result. And the last task was the Brixton test, but adapted to ID patients. So basically, a black circle is moving, and you have to predict where it will go next. So if it goes from there to there to there, then you have to anticipate where it will go further. And what is interesting is that the rules can change during the test. So just to show you an example, here it is. So basically, it's a participant. So it goes this way, and then suddenly it changes, and you have to anticipate that if it changes, you have to understand implicitly the rule, which is interesting. So we did validate that also on more than 100 participants. So using this way to the maximum level of rules, because it goes more complex. They of course they had trouble to go very further, but a lot of them were able to go further. The only thing is that to have the rule acquired, we define that you have to make no mistake for the last two repetition of the rules. So we'll see if we can just find a different way to analyze the data, because we have the impression that they could understand a little bit if they were able to keep going. So here, just an example. I don't know if you can hear the sound, but basically, if the sound is working on your side, you will see that it's the same. I mean, it's a Zoom video, and you can listen to the birds, because the patient is on his, it is at home, and the garden is there with the sun and the birds, and it does that very well. So the reproducibility was really good during the different tests. We used PPVT5 to test the language abilities. So the child had to point to the picture that matches to what was said, show me to get dressed. And what is really interesting is that 19 out of 20 patients were able to do that. So this regarding the receptive language is really very interesting, I think, in CTD patients. It was very much more difficult to use EVT3. The beauty of it is that you can compare, because it's basically you can assess the receptive and expressive language using something which is comparable, but only 13 out of 20 were able to do it. And then, so we did also do some motor assessment. I will go a little bit faster because I'm behind time. And a kinematic task where they had to take an object and to insert it in a little shape. And you had different conditions. What is very interesting is that they were able to adapt the size of their grip aperture to the size of the object they had to take, and they adapted the effect of the movement time was on the second part of it for the small base, which was a more difficult condition. And just to finish, I will show you the results for the first time too of the eye tracking data. So the first one were just to see if they have a social preference using movies. So we just display on the screen two clips side by side, one social, the other non-social. And it's very simple because it's implicit. They do not have anything to do. They just need to be able to, to be able to do the calibration before the eye tracking, which is not so easy for some of them. But then it's very implicit, and they just need to watch the movie. And then we define social and unsocial area, and we were able to compute the time spent on each type of region of interest with data on more than 50 LC controls. And as you can see, the youngest children really had this social preference. And here's the result for the CTD. So it's interesting because there seems to have the social preference. Nevertheless, we need to be careful because their total time of observation was really less than what we expected in neurotypical children. And the really last thing I will show you is the fact that we show them social scenes. So what is interesting is that you have characters that are interacting one with the other, and you have also objects, non-social objects that can be interesting to watch, to look at, but that are non-social. And we were able to compute, of course, here is a heat map. We were able to compute the time spent on the characters versus the time spent on the objects. And on CTD patients, you can see that they spent more time on social than on non-social. But when we compared with neurotypical, we can see that the neurotypical kids spend even more time to social than to non-social. Which is interesting is that it seems like they had similar behavior regarding the non-social, but the typical kids looked a little bit more. So it's interesting to compare both type of stimuli. To conclude, so this new outcome measure that we designed seems to be really targeting a core ID dysfunction, reasoning, inhibition. They are appropriate to ID patients with different difficulty levels, and they were validated in healthy children above 3 years and adults. And the idea is that we were able to provide objective and quantitative assessment. The tablet assessment can totally be carried out at home without any trouble. And the beauty of iTrack is that when you design very simple tasks, you do not need to have, you can use implicit instruction. So that's interesting. And we hope that this will be used as biomarker in future study on CTD. I really would like to thank all the families that were really wonderful. It was a real adventure for the whole team. And of course, all my collaborators. And I would like to thank also Extraordinary Association and Serious Brain Therapeutics that provided some funding for this study. Thank you.
We have some question from home.
Yeah, so the first one's from Vicky. Why are all the studies only conducted under the age of 25? Dr. Miller suggested behaviors seem to reduce after the age of 25, where there's no, where is this data as no study has been done with CTD patients over 25. This is not what the community are experiencing, and where they are reducing, we the community believe this is due to a lack of energy, mobility issues. By removing outcomes like behaviors, writing, we are missing areas which you will see more improvements in CTD, in my opinion.
So I will take it slowly, one
yeah,
minute at a time, if you don't mind, because it's a large question. So, so why are the studies only conducted under the age of 25? Only because the oldest patient, I think it was 26.7 years old, so mainly 25. We could have included patients up to 35, but I'm of course dependent on a participant that can be, between 25 and 35 in order for them to be included. So no other patients ask me to be included, otherwise I would have. Why did we check and why did we at first the answer is, would you mind to just let the
Sorry.
Okay, no, it's fine. I will remember. So basically what we first decided that we did want to be sure, in many, in a lot of different diseases, not CTD but others, we have noticed that after a certain age there can be like aging that can happen. And the goal of this first study was really to capture the phenotype of CTD patients without having this confusing factor. I'm not saying it's not interesting. I am very interested in it. And to tell you the truth, I've already met a patient that, because he was the uncle of someone from the study and he was 53. So I am not saying that it's not interesting to look at CTD patients that are older. I'm just saying that to start with, it was important for us to start with a certain age range in order for us to have the more, like homogeneous data. Dr. Miller suggested behavior seems to reduce after the age of 25. Okay, so I think we have to be very cautious because I mean, Judith, tell if you do not agree with me, but in my opinion, in my knowledge, to my knowledge, they do not have a lot of studies looking at older patients with CTD. So we have to be, it's true that sometimes we have like outbursts of behavioral problem during adolescence and young adulthood, but it does not mean that after 25, there is a strict limit, and I think it's, no, I will not dare to say that. Okay.
It's anecdotal, but we just hear from families that the hardest part gets better. We also hear some families when their kids are in their 20s, their speech increases. We've had a couple situations like that, but it's, adults are not diagnosed as often as kids, and so there's not that many. It's not as easy to do a study on adults, at least traditionally.
Maybe moving forward, we can focus on that as we enroll more subjects, as we start to follow them longitudinally. But for now, it's just anecdotal.
Yeah.
And then the other question is, Dr. Curie, we really can relate to our son refusing or struggling to do simple tasks, but then being able to do seemingly more complex tasks, as your results show. For example, when he's reading. What do you put this down to? Behavioral, anxiety, frustration, attention?
My first answer would be a lot of them were impaired by their inhibition abilities, the lack of inhibition. Like they can do some things, but when, for example, it's typical, at our hospital, there is, I did not notice before the study, to tell you the truth. So the patients made me aware of a lot of things. But basically, we have a site where we can see the bus coming, you can see cars going through, you can see an helicopter, landing. And of course, if there is anything like that, the child is going to be more focused on something else, and attention problem is, I think, something that can really impair them. Let them have more trouble to perform the tasks. So yeah, we did. I would like also, I among the collaborators that really contributed to the study, I really would like to thank Marion Buchy and Farah Gerbi, because both of them, and a lot of students that contributed also to the study, but and the researchers, of course, from my team. But it's really important. We really have adapted everything in order for the patients, we do not follow a strict order. Basically, we did what, and we are doing what is good for the patient. So we take a pause, we change, the order of the task, because we have the feeling that he's a little bit more tired. We are doing, speech assessment, and then it's getting too complex. So we switch with some more motor. These kind of adaptations are really, I think, very important for them to be able to do it.
Okay, I would like to thank Aurore again, and we are taking a short break. We come back in.
Great. Thanks so much for having me, and with this great group and the Boston Children's colleagues and the people who just presented. This is going to be hard to follow, because I'm going to do the less glamorous work of kind of pulling the curtain back as to why we're doing certain measures and what these natural history studies are really supposed to help us with in terms of getting towards clinical trials, and what we are learning from them and about our measurement to try to get us to that place. So I'm a psychologist. I was involved in following the patients at the NIH portion of the VIGILAN study, and I've also had the very great pleasure of working with Heidi and the team very closely on the PCORI grant. So my views today are from both angles, from certainly knowing about the measures and the kids, but also the work that we're doing with the parents and the questions that are being asked about getting a core outcome set, and then getting from core outcome sets all the way to actual measures that we can use in a trial. I first, whatever condition I'm talking about that I am studying or thinking about at the time, I just want to always raise the issue that almost everything, there are absolutely unique things to CTD, but I think the good news is that there are so many genetic conditions being identified and studied in natural history, and Mustafa showed this morning, a lot of us are doing this collaboratively for multiple conditions, and a lot of the lessons learned are actually from seeing across conditions similar problems, and that helps us when we see similar problems across conditions. So just the importance of joining together and efforts that I know CTD is the foundation is thinking about to make sure that you're not doing it alone, because unfortunately the numbers are never quite there to do some of the work that needs to be done alone. And also because for the FDA and European agencies and for regulatory groups, the issues are the same across. So again, Dr. Miller presented the VIGILAN study and the results. And I just wanted to, again, point out that the purpose of this study was really to enhance our understanding of symptoms for the idea that there, as therapeutic interventions are being identified, what we really need to do is make sure that we have endpoints relevant to CTD for those studies. To be able to understand what is improvement and clearly what is clinically meaningful difference to families in those areas, in improvements that that will make a difference, not just to get a drug approved, but also to really understand what the outcomes are for this population that are of interest. So I put on here what the FDA actually puts as the roadmap for outcome measure development for clinical trials. And I think I really hone in here on how to conceptualize treatment benefit, how the FDA does. And for some conditions, it's really about survival. For other conditions, it's about how the symptoms feel to the patient when you're in pain. Is there less pain? And clearly that can be relevant to CTD. But the third area, which is clearly relevant here, is functioning. And we'll come back to this because we actually have been, all the studies that you just heard about have been measuring adaptive functioning, which is really about functioning in the real world, which the parents in the PCORI effort really did state as a major important outcome. So just keeping that front and center is, there's joining together of what regulatory agencies want, what we happen to measure anyway, and what parents are indicating as important outcomes. So it gets a little harder though when we figure out how we can do this, because FDA really likes when it's direct measures of treatment benefit, how the patient feels and functions. It may not be possible. So this paper is from this figure is from a paper about rare genetic conditions where we know there is intellectual disability, where we know that we may not be able to get directly from the patient interviewing them how they feel, how they're functioning, how those changes are. So when we're not able to get at direct measures, we have to worry a lot about making sure that they're valid in many different ways. And so I just introduced you to the lingo because I think it's really important when we don't understand why the FDA isn't approving something or why a study even doesn't get approved for looking at things, what their lingo is. So they talk about patient-reported outcomes as the gold standard, that the patient says, I was in pain and then I'm in less pain. Performance outcomes, which we did just see a lot of, which includes some of our IQ tests, some of those amazing iPad tests we just saw, even the test of eye tracking, how they're moving. But these are tests where it's directly measuring the performance of a participant. And then we have tests that are a little more removed, which could be either observer rated, which we do consider our interviews of adaptive behavior to be that, or clinician reported, which would be the clinician stating if the patient is getting better based on a global impression or things like that. So I just wanted to make sure that we're thinking about this lingo when we're thinking about it. But I'm mostly going to focus now on the neurodevelopmental outcomes that we knew about before VIGILAN. So this was really the only paper that we knew existed before, which showed us some really good information about language level. So we really did get a good indication that there were, you know, a significant portion of people with CTD that did not have any speech or fluent speech. And then also that there was intellectual disability to the degree when we see this, that IQ, you know, as was pointed out in the last talk, is below 30 or 40, we know that a lot of our tests are not able to actually give us standard scores. And I'm going to talk more about that in a minute. So these were clues that we had that our regular repertoire of tests were not going to work. Regular meaning tests used typically in kids. So as I said, we saw this significant speech delay and many people not having fluent speech, the pretty much universal intellectual disability. And we did already see a signal of decline over time, and that a lot of it was in the moderate to profound range. So these are tests that you've now been hearing about a little bit. The adaptive behavior, which, well, it says proxy report, meaning it's from the parent, but we're going to consider it to be observer report because the parents are observing them. And these are the areas that the test measures, which, you know, we've heard a lot about today as important areas that we know parents and individuals themselves are interested in improvement for. And then we've got the IQ tests, which are performance-based tests, which we know the FDA is looking for, but they have some problems with them. And we also don't really know how they map onto this functioning. We do have correlations, but we don't really know how they do. And I'm just going to get into some of the details now of that. It's difficult to identify the constructs that are relevant to the entire population. Again, we saw that early natural history study, or not natural history study, retrospective report that we saw with data was really when there weren't that many people identified. We are now seeing more and more people identified. We're seeing the functioning range differ a lot. So we know that we probably need a large arsenal of tests to give the full range of functioning that we may see, which is why we end up having to use multiple tests, especially when we have multiple age ranges and multiple levels of functioning. So these are some of the tests that you may have seen or heard about. The problem with these tests is that, so the Bailey and the Mullen are for younger children. The DAS is a test that covers a larger age range. The Stanford-Binet covers an even larger age range. The lighter, which you heard about, covers a larger age range, but a lot of them don't cover the whole age range. And then a lot of them also don't cover the full range of functioning, as the tests weren't developed this way. So this is how they are. We just heard about how the lighter is another test that also goes below 40, but very few tests go up under 40 for standard scores, which means that everyone getting it, or at least the children who are not able to get those scores, will be scoring at the lowest range at their first time point, their lowest range at a second time point, their lowest range at a third time point, even when they may have developed skills. So again, we look at these tests as sort of, some of them are considered developmental, some of them are considered transitional, not quite IQ tests, and then some of them are considered standardized IQ tests. And as you can see here, this just gives some examples of the different levels of functioning needed to even get on the test, which is why it was so exciting to see the French study be looking at matching to sample, and we're really interested in that too, as a metric of sort of getting on, being able to do some of the performance that you need to do on the tests, and it really as a pivotal skill that that we want to see if we can get going to help us so that we can see improvements on all the other skills. But you can see here what happens when these tests are not built or developed for this kind of population is, this is from some autism work, is that over time, as kids get older, their scores go down over time. And when we have to use ratio scores or scores that are contrived because we don't get standard scores, it's it's really a problem. So even though scores are going down over time, when you look at mental age or raw scores, you see the kids are actually developing skills, but you just aren't able to see it on the tests. Let's see. So, that's why these developmental constructs are more challenging, is that we have two choices. We can either assess a very narrow age range with more detail, but then we get poor validity, or we can assess a broad age range with less detail, which is really a problem for looking at responsivity when we're looking over time. And so this is another example, and this is from adaptive behavior, and this is sort of why we've been able to focus on some new kinds of metrics more recently. This is just with Fragile X over time. You can see that on adaptive behavior, it looks like they're declining, and that's all because of this standard score problem. So this, I just wanted to take a teaching moment to really show you some of the properties of some of these different metrics that we get from a test that allow us to see that even though tests that are developed to not show change over time, because they were really developed just to diagnose, can be used in different ways to show change over time. And so the standard scores do what I was just showing you. They go down over time when ability stays the same and you get older, because you're always being compared to peers. And as your peers improve rapidly, and you're on a different trajectory, you're never going to be catching up to the point that your standard scores even stay the same. Then we've got raw scores, which the FDA has seemed to like a lot, because you can imagine a raw score is actually the items on the test that people are doing differently, either getting better or worse. The problem is that they're not on an interval scale, so we can't actually map them one-to-one. It isn't like linear, and they're also very idiosyncratic to the test. So some tests have a lot of items at the lower end and then go really fast up. Other tests, have a few items at the bottom and then go in different ways. So we just, it's very, very, very hard to change. We can explain it to you on a one-on-one basis, but it would be very hard to have in kind of clinical trials. So then we've got this third kind of measurement or metric, which is called a personability score, which is not related to how you're doing compared to other peers. It's not a very meaningful number like a standard score, which is a mean of 100, but it is showing the change over time. So what might be helpful for diagnosis, like the standard score, might not be helpful for these trials. And so we need to use different metrics that we're not as familiar with, and that might not make as much sense intuitively for these kinds of studies. And Dr. Miller showed you this. So a child who, this is the standard scores, the 20 is the lowest score, and this is what they look like, can actually have these personability scores or gross scale values that show that they're actually doing some of the items, even when it's profound intellectual disability, even when they are only doing a few items. So this was early on from the VIGILAN trial, when we were just starting to look at the data. We were actually the first, this Creatine Transport was one of the first to publish these gross scale values from the newest version of the Vineland, to really look and see, are we still seeing these kind of floor effects? So here we can see that we had a floor effect of expressive language. A lot of children got on the lowest level for what the test gives, which is a 1 for expressive language, but we did see variability on the gross scale values. There were some areas like domestic where we did see even some sort of basal or floor effect on the gross scale values as well. But even for that, we did see, as you can see, a bunch of variability here. So this is sort of, there are the graphs that Dr. Miller showed you that we saw change over time. And this is just showing that they were meaningful in this population. And so I'm going to actually just end early and I have a feeling there will be questions from this. And just to say that, it's really important for these natural history studies to use these kinds of measures that actually can be used in the clinical trials. And sometimes we miss and, we don't know, because we're learning about the population at the same time as we're learning about the measures. But other times we hit, and when we hit, we actually can use the data from the trials as what we call external control data. So that if there's going to be a trial that is going to be a small open label trial to look for safety of a intervention, for instance, and we really can't get control data, we can use the data from the natural history study as a control itself. And the FDA has been somewhat open to doing that. But we always need to be just really wary of the limitations of our measures, and which is why I think you saw in the study from France that sometimes we just know that the measures that we have are not going to do everything. So we actually need to develop our own measures, which puts us back a little bit because we need to start from scratch with validity. But we can, at least when we are developing our own measures, develop them specifically for the population. And then, of course, we need to use multiple measures when necessary with systematic plan to combine. And this is where we thank the families so much for their time and effort. And sometimes we actually have to use multiple measures even within the same domain, because we need to validate that one, especially a new measure, is going to be correlated to a measure that's existing or that the FDA has already used in a trial, because that's sort of how they work, sort of like maybe like the court system on precedent, is that they know what has worked before. And so when you make changes, you have to show how it correlates to measures that have already worked before. And then we just have to really, really think about metrics. And like I said, the same metrics that might be helpful to a family for looking at a diagnosis, or, you know, even what might be useful for schools or reports for services may not be the same that are useful for studies. And that gets really confusing because we want everything to be useful clinically in the here and now, as well as for our studies. But I think we're finding that that's not always the case, both with the measures we use, which is why sometimes they're more experimental, but also even with the numbers and the metrics. But we need to be able to explain all of this to families and the patients themselves, as well as to the regulatory agencies. So I think that's all I have. And again, thank all the collaborators here who have been working on these big efforts, and certainly to the families that have contributed to this knowledge.
Thank you, Audrey. So is there any question from the audience here? I do have a question for you, Audrey. For example, we have seen from France new methods, very like almost a game to measure cognitive function. It seems quite effective. The kids seem to be engaged with some caveats, but they were able to perform. How easy would it be to adopt that type of testing across the multi-site that you are having here in the United States? Because there is always that, oh, it's great, but we need to validate, it has to be published, has to be blah, blah, blah. It takes years to do that, when instead maybe implementing right away would allow to collect significant data that can then be maybe sensitive to interventions.
Yeah, I think that's going to be absolutely essential. And I was so amazed to see all the work that's gone on. And I really do think we need to leverage it from each other and not recreate the same wheels. I think some of the tests obviously have language barriers and things like that. But I think with this population, some of the nonverbal or, you know, sort of visually based tasks that I think we've been working on and you've been working on, I think really could be done across sites. And I think that helps establish the validity. And then certainly we need to be looking over time.
But how quickly can they be adopted for, let's say, tomorrow there is a clinical trial. Unfortunately, we are not there, but if there is a clinical trial that materializes quickly, if we have not published yet, no, because there is a developing and validating the outcome measures, can we still consider such positive outcome measure to be accepted for a clinical
well, I will definitely defer that to the regulatory agencies, but I can say for sure that, you know, that it certainly wouldn't be a primary outcome, but whether whether there's enough data to establish something as, you know, exploratory is possible, but they definitely do want to see data, and they want to see it over time.
Yeah. Okay. Okay. Thank you. Any other questions?
There's one that came in online.
There is one online question.
So Vicky is asked, says, in the UK, my son's school's using a system called P levels, which was the first assessment tool that could show his progress. I appreciate what you said about using school assessment tools, but this may be the only way, as my son's difficulties were too complex for the assessment you mentioned, as he was deemed mentally 2 years old until he was the age of 13.
Yeah, so I think we need to learn from the parents. We need to get that information about the assessments that are working and see how we can, you know, map them onto our tests or develop new ones. So I'd be really curious to hear more about that.
So this is a strong encouragement for the parents to speak up and also to communicate with the scientists, because otherwise, you know, it becomes only anecdotal at this moment, but then we would need some follow-up to really learn.
Yes, but and again, to give enormous credit to Heidi and the team, a lot of the people who've spoke this morning from the foundation who you know got a grant and have worked so hard and are working on. They were working on the part about what are the most important areas, domains, and now they're really hoping to work on this next piece of mapping those domains onto measures that will be mutually helpful with the properties that I'm talking about, but also seen as helpful directly to the families.
Any other question?
She sent a thing, but I'll send it along to Audrey. The link about the feedback.
So the family who wrote this question.
Excellent, excellent. I can't wait to.
That's what we want, to connect people. Okay, thank you so much, Audrey. And now we pass to Samar Rahhal from NIH again, and she's a neurologist working with neurodevelopmental disorders individuals, but specifically she will give us an update on biomarkers, hopefully different kind of biomarkers, both functional and fluid biomarkers. So looking forward for the presentation. Thank you, Samar. Thank you for being here.
Thank you for having me. Can everybody hear me?
Yes. Yes, but you're not in presenting mode.
Yes, let me do that real quick. Is that presenting mode?
Perfect. Yep.
Okay, great. Okay, thank you again for the organizers for having me today, asking me to speak. I will be talking about biomarker findings and the potential use of functional near-infrared spectroscopy in creatine transporter deficiency. So this was reviewed earlier this afternoon, and I'll go through it real quick. Just as a reminder, there are two sources of creatine in the body. One is through ingestion and the other through peripheral synthesis. Ingestion is a variety of foods, but there is also a big component that has to come from peripheral synthesis. It's a two-step process facilitated by the enzymes AGAT and GAMT, which is two of the creatine deficiency disorders that we know. And the production ultimately is of creatine. Creatine goes into the blood, and uptake from the blood into organs that need creatine, such as the brain and skeletal muscle, occurs and is facilitated by the creatine transporter. The creatine transporter also has a role in ingestion of creatine, helping with the ingestion of creatine, and also with renal reabsorption. So its primary goal is to make sure there's enough creatine in the blood and also to have uptake into the tissues that need it. Creatine is important because it is a source of energy for the body, and especially for the brain that needs immediate sources of energy because it cannot store energy. So between the creatine phosphocreatine system and the release of phosphorus, ADP can be converted to ATP, which is the major source of energy for the body and tissues. So with that in mind, I will go over the two biomarkers that had implications in our findings today. So the first is called amyloid beta, and it's a small protein that is composed of about 40 amino acids. It's actually produced by the cleavage of another protein called the amyloid precursor protein that you see right here. This is a transmembrane protein that is present abundantly in neurons, and it is cleaved twice, once by beta secretase and the second time by gamma secretase. Depending where gamma secretase actually cleaves this protein, you can get smaller or larger, longer, basically, peptides. And the longer peptides tend to do aggregation and form something called plaques. For the longest time, and still more or less, the amyloid hypothesis is active in Alzheimer's disease. It states that when amyloid beta is overproduced or not cleared efficiently by the brain and the surrounding tissue, this causes aggregates that you can see here on your screen. These are thought to disrupt communication between cells and activate immune cells, which can cause inflammation and trigger a neurodegenerative response. It's now understood that amyloid hypothesis is not the whole story behind Alzheimer's disease, and that's for various reasons. But one of them is that there have been numerous studies that are targeting these plaques for Alzheimer's disease that have not shown the best outcomes. But what is interesting is that amyloid beta 42 and also the ratio between amyloid beta 42 and amyloid beta 40 is used to diagnose Alzheimer's disease. And so when amyloid beta 42 in CSF is found to be decreased, this is very suggestive of Alzheimer's disease. And this is thought to be a consequence of amyloid deposition in the brain. As amyloid beta aggregates, there's less to be spilled out into the cerebrospinal fluid. The other biomarker that I will go over quickly before I show you our results in our study is tau. It's a protein that has an important role in microtubule assembly and stabilization. I have a picture of a microtubule there. These are structures that are inside the cytoplasm of cells and that help with cellular cytoskeleton and integrity of the cellular shape. And tau is an important protein in their assembly. However, also when found in excess or when it is not in healthy tau, it can aggregate into filaments in what we call neurofibrillary tangles that exist inside the neurons and glial cells. Tauopathies are actually a group of neurodegenerative disorders where these neurofibrillary tangles are found inside the neurons. What happens is that tau, because of its inability to bind to microtubules, affects the integrity of the cell and the health of the cell in general. In Alzheimer's disease, tau levels are found to be increased in the CSF, and they actually have prognosticating, they are usually used also for prognosis or to figure out the severity of the disease. So the more tau is present in the CSF, the more severe the Alzheimer's disease is found to be. So back to our findings. So thanks to the IRB-approved VIGILAN observational study of CTD, the 4-year natural history study that we just heard about from Dr. Miller and Dr. Thurm, we had cerebrospinal fluid for individuals who participated in the study. We only had one sample over the course of 4 years because that's how the study was written, but we were able to obtain this for evaluation, these samples. And of course, we needed a comparison sample. As you can imagine, it would be difficult, if not impossible, to get cerebrospinal fluid from healthy children. So instead of that, we obtained a comparison sample comprised of CSF from Smith-Lemli-Opitz disease patients and participants who were here at the NIH for a different disorder and a different natural history study. And we used those as part of our comparison sample. We also had access to CSF from pediatric patients who presented to outside emergency rooms, and also we had some of that. So we put them together as one comparison sample because their levels were very close to each other. So we also had, as part of the natural history study, we heard about this quite a bit also earlier this afternoon, data from Vineland Adaptive Behavior Scale, the Adaptive Behavior Composite Score, ABC for short. And this is a scale, of course, like I said, we heard about it, but it looks at daily skills and daily living tasks and how the participant is able to adapt to their daily environment. So it's a useful scale in that sense. And we use that in order to correlate, as I'll show you in a minute. So we had 12 individuals who had cerebrospinal fluid available for analysis, and these are their ages. And then for the comparison sample, we had 23, and their ages were a little bit older. Our ABC score for our CTD participants was between 20 to 69. I believe about 100 is the more typical or average number. And then 58% of our CTD participants had seizures, which is goes along with what is known about the disorder, as opposed to none of our SLOS participants. Unfortunately, our pediatric controls, we didn't have that clinical data for. And these are our findings. I'll walk you through them. So the first chart is our total tau. The circles in red are our CTD participants, and the blue squares are our comparison sample. You can see that using t-test that we found statistical significance for all three of the biomarkers when we looked at the average for total tau, for A-beta 42, as well as A-beta 40. We also looked at the ratio of A-beta 40 and A-beta 42 because there's a lot of literature on that ratio, as in some disorders, they go, one is increased, one is decreased, or one is normal and the other is decreased. So we wanted to see if there was any of that effect, but we didn't see that in comparison to our comparison sample. We saw that they were pretty much similar. So these are our findings as far as the biomarkers separately. We then took it a step further and used those Vineland ABC scores that we had that were done at the time of the CSF. So it would be the same time. And we found, as you can see, an inverse correlation for all three of the biomarkers, so that when the biomarker levels were higher, the Vineland scores tended to be lower. If you notice in each of the graphs, there is a black circle, circle at the bottom. This was an outlier that we are not able at this point to explain. So this participant had both very low Vineland ABC scores as opposed to the rest of the sample, but also very low biomarkers. So we did check on the CSF to make sure that it was valid and the protein and glucose values there were normal. So we weren't able to explain exactly why this participant did not follow everybody else in the correlation. So in conclusion, for the first part of my talk, we found elevated levels of A-beta 40, A-beta 42, and tau in CSF of individuals with CTD, and we found that this inversely correlated with Vineland ABC scores. In order to try to explain this finding, we know from the other literature that altered bioenergetics, so when the energy balance is altered in the neurons or in cells, this can affect APP processing. And we hypothesize that neuronal creatine deficiency results in energy deficiency in the brain, because creatine, as we said, is involved in energy utilization and storage as phosphocreatine. And alterations in the system may therefore result in cerebral energy depletion. The elevation seen in biomarkers may be a reflection of altered cerebral energy status. It's important, though, to note here that simply having elevated biomarkers in CSF does not indicate that there are plaques or neurofibrillary tangles. In fact, our findings are a little bit different than what's found in the Alzheimer's disease literature because our ratio is not altered. And they're both elevated at the same time. So in the absence of neuropathology data, we're unable to make the leap, and we caution against making it. I will move on with the second part of my talk, which is another biomarker for CTD. And this is, or can be, a biomarker for all the creatine deficiency syndromes. And this is functional near-infrared spectroscopy. I know that Dr. Baroncelli is going to be also talking about this at the end of the afternoon. So I'll give you what we found and what we've been doing at the NIH, but hopefully not taking over too much of what she's going to speak about. So functional near-infrared spectroscopy is based on the premise that the brain is a high energy demand organ, but at the same time, it's unable to store energy. So when neuronal activation is required, cerebral blood flow occurs immediately. And this is called neurovascular coupling. This is the basis for functional MRI, PET scanning, and also FNIRS. So what FNIRS does specifically is it measures regional tissue oxygenation. Optical sensors are placed on the scalp, and these emit near-infrared light. It propagates several centimeters through the scalp and skull. And we know that hemoglobin, which is present in the blood, is a significant absorber of near-infrared light. A detector is placed a few centimeters away to detect the light that's reflected back, and changes in the amount of diffuse light reaching the detector provides a measure of changes in cerebral hemoglobin concentrations, which indirectly will also give us a measure of cerebral blood flow and brain energetics. This is what the machine looks like. As you can see, there are wheels, meaning it's portable, which is a major advantage. And all these wires connect to a cap that is placed on the participant's head. It feels like a swim cap. It's cloth, and it is pretty snug on the head, but it's not painful. And then the wires are attached accordingly. The advantages, like I said, is that it's portable, it's non-invasive, so there's no radiation involved, and it's cost-effective. And although the participants can't really be dancing around the room, there's not a strict restriction on motion as you would find, like, for example, in PET scanning. So they can still move around in the chair at least. So that's an advantage. But disadvantages is that there's limits in the size of the brain area that can be measured. The cap is, not very big, and there's only a limit to how many optodes can go on there. Usually we do the frontal. Can only detect near-infrared light that penetrates the first few centimeters of brain tissue, so it doesn't go deep inside like an MR would. And then there's no anatomic information. There's no CT scan. There's nothing to look at the anatomy. But it is used in multiple clinical scenarios. And, I list them here, but there's also many more. So what we wanted to do at the NIH is look at the use of FNIRS in neurocognitive disease. We have several natural history studies, and those involve neurocognitive disorders where compliance is an issue. And so getting things like a functional MRI would be difficult, to ask the participant to sit still for a long period of time, etc. So we were trying to see if this FNIRS would give us similar information in a much easier, much simpler way. So our primary objective for the study is feasibility. Is it even feasible? Is it something that our participants, our patients, our population would be able to handle and tolerate? And again, from that, our secondary objectives would be to determine the patterns of cerebral oxygen consumption in neurocognitive disease as measured by FNIRS, and to compare that to healthy volunteers that are age matched to see if there are any differences there. We're including males or females greater than 6 months of age. Recently, we are looking at adjusting that to about 5 years because we're finding that the very young, it's been a little bit more tricky. But right now, the protocol does include over 6 months. We do English as primary language only because neurodevelopmental testing is also part of this study, and we needed to make sure it's standardized across the board. And then we do say that we do include all of the disorders that we have natural history studies for, Niemann-Pick disease, Smith-Lemli-Opitz syndrome, and others. Creatine Transporter Deficiency, as you all know, we don't currently have an active natural history study for, but we did include it because we have, and participants with CTD are certainly very welcome to join the study. So, and we would love to have more of them. So our exclusion criteria would be any reason why there's a skin disease like psoriasis or extreme eczema, that it would be, the cap would cause sensitivity or any sort of reaction. Any vascular disease like stroke or high blood pressure might affect blood flow in the brain and might affect our data. And then any traumatic loss of consciousness in the last year. So exclusion criteria are, few and unlikely to be seen very frequently. The way the study works is a very simple study. We do a history and physical examination on everybody. We do a neurodevelopmental assessment, like I mentioned earlier, on everybody. And then we do the FNIRS evaluation. So the FNIRS evaluation takes place in a quiet room. Families are welcome, one parent usually, to be with a child. And then we do 2 evaluations, one in a complete resting state, where the child's asked to sit for 1 to 3 minutes, preferably 3 minutes, staring at a screen that's not really doing much. So it's more boring than anything else, is what I tell families. And then for the next 3 or 5 minutes, we do a listening task or a visual task, which is considered an active task to see if there's any differences in oxygenation and blood flow from the resting state compared to the more active states. So we don't have data right now on our results, but we did look at feasibility really quickly. At this point, we have about 29 affected participants. You can see there was one with CTD. We'd love to have more, like I said. And I know with our collaboration with Boston, we hope to get more soon. So the age ranges here were from 3 years old to about 31 years old. And then we split to see if to see our data in the resting state versus the auditory state. You can see that about 48% were able to do the resting state versus the auditory task, about 42%. And some of the reasons are difficulty tolerating the cap. Like I said, it can be snug. We try to distract as much as possible. Another reason is that we have a lot of very chatty patients, and they do need to be sitting quietly, but they want to talk or they want to vocalize. So, that can also interfere. Those would be our top two, I think, reasons why I would say the cap and the ability to tolerate the cap for as long as needed has been a little bit of an issue sometimes. I will point that one patient did fall asleep. And like I said, it is boring, so it's not painful or really all that uncomfortable. But that was a problem when we were trying to do an active task. So in conclusion for this part of my talk, FNIRS is a promising modality that could help with our understanding of the underlying pathophysiology of neurocognitive disorders. Of course, the first question is to make sure that it is feasible. And there are a lot of ways that we can help, make it easier to tolerate. And then, the most important thing is that it can serve potentially as an outcome measure for future treatment studies. As we heard earlier today, there's always a need to look at biomarkers. And finally, before I take questions, I did want to introduce yet another study that we're doing, and this is specifically for CTD, and I would love to be contacted about the study. So the objective is, and I think we heard earlier from Dr. Anselm today, that there are certain features, facial features and other features that can be characteristic of CTD. And it's important to recognize those and to characterize those because once we do, we are able to educate and disseminate to pediatricians and developmental pediatricians, and so to help them identify characteristics that would help them think about CTD and pursue the diagnosis from there. So it does help with raising awareness, which is always a goal for having more studies and more research. So it's simple enough. We're looking for males with CTD, genetically confirmed, and all we want to do is look at pictures. So if the participant has been at the NIH, we actually already have the pictures, but we want to send them to our partnering researchers at McMaster University who do morphologic studies and who look at dysmorphology, so that we can have it done in partnership with them. So in order to be able to send pictures to them, we would need to do consent. So even if we have pictures, we would need consent for these pictures to be sent. And if we don't have pictures, then the study would ask the individuals to take pictures of their children or of adults and send them to us, of course, securely, so that we can send them on to McMaster University. So we would need consent for that. So I just wanted to introduce this study also at the end of my talk, and then take any questions.
Samar, any questions? Yes, we have one question from Heidi.
I have a question, Dr. Rahhal. My understanding was that the dysmorphic feature study was not open to patients that were not a part of VIGILAN. So I just wanted to make sure I understood your comment about sending in pictures. Is that still only restricted to VIGILAN patients, or does that open up now?
No, you don't have to. As long as genetically confirmed CTD, we can accept pictures from anybody. Yeah. But we would need to look at that, we need to just confirm the diagnosis, obviously.
Thank you.
And then do you do 3D reconstruction of the features of the face, or do you do only 2D? Your pictures will be only 2D.
My understanding is 2D, yes.
I have one more question, sorry, about the fluid biomarker. Did you look specifically about tau and the amyloid beta 1442 specifically, or did you look at everything and like you did a profiling and those were the only things that were changing? The question is, are they the only things that are upregulated, or there are other proteins, transcription factors? That
there were other factors that we were looking at, and those were the ones that showed up as elevated, yes.
Wait, I just have.
We have a question online.
Someone just asked, can we share this in community about the picture request? That there would be a lot of pride parents.
Definitely, and I believe Heidi has information on that.
Yeah, if you have updated recruitment materials on that and can send them to me, that would be great. What we had received and posted had said VIGILAN only, so I'd like to get the word out. That'd be great.
Okay, absolutely. Yeah, I can talk to John and we can get that.
Okay, thank you so much.
Thanks. Yeah, definitely.
Okay. Okay, now we switch a little bit gears and we move from human studies to animal models of CTD, and we are very happy to have Matt Skelton here with us from Cincinnati Children's Hospital, and we will talk about understanding the mechanism of function of the transporter. Thank you so much.
All right, well, thank you for the invite. Very pleased to be here. When Laura emailed me, she proposed this title, and I kind of ruminated on it for a while, and I actually like it, and I'll go through and sort of explain why here. First things first is the acknowledgement slide. This is everybody that's helped with the data that I'm getting ready to present, so that we can get to the mechanisms behind CTD. So one of the worst things that you can actually hear as a behavioral neuroscientist when you're getting a grant review or a paper review is, what's the mechanism? It turns into Hulk smash. I mean, it really is. It's awful. Okay. But how do we actually know what a mechanism is? So we start with an observed phenomenon, right? We start asking questions of what, when, where, and how. Problem then becomes, those become the observed phenomenon, and we have to dig deeper, right? So that's where we're sort of at right now. So that's where we're looking at as we go through these. I'm going to kind of keep going to the when, what, and how, when, where, and how of the phenomenon that we see. Why does it matter? So we know that the lack of creatine causes intellectual disabilities. And, we sort of have an easy target, just get creatine in the brain, right? That's what we thought 24 years ago when we started this. So one of the biggest problems is that we have this big gap between animal models and humans, is that we have things that work in animal models that don't work in humans. One of my other interests, aside from CTD, is mental health disorders. The gap there is huge. There hasn't been a new drug for schizophrenia in 60 years. That's the problem that we continue to have. Some of these is because we have bad mouse models. So the other thing is we can identify things that are disrupted by CTD. Maybe we can target those instead of this problem that we're having of just getting creatine into the brain. So that's another aspect that we started thinking about. So what did we know about creatine in the brain prior to the discovery of CCDS? Now, GAMT was discovered in 1996. I honestly thought about leaving the slide just like this, but we knew that creatine was in the brain. That was it. We used it as a marker for MRS. to compare N-acetyl aspartate, whatever that does, and other chemicals that we saw on the spectrum. So my story of being involved in creatine, as many of you know, goes way back to when Dr. DeGraw discovered it. He tasked my postdoctoral advisor at the time to generate a creatine transporter knockout mouse. They had tried at Vanderbilt, not so successful. This is a tough gene. I mean, and I think that Laura can back this up on, and it just is a tough, every time you try to manipulate this gene, you run into roadblocks. It's a very funny gene. Anyway, so we had two goals. First goal was to develop a high fidelity model that we could test treatments in, right? The other one is we wanted to answer basic biological questions about what creatine was doing in the brain, because we didn't know. We knew that it was important in exchanging ATP, which is another sort of black box of the brain. It's this idea of manipulating ATP. It's a very difficult field. But what we really wanted to do was develop a model that allowed us to better understand why this lack of creatine led to such profound neurological deficits when that wasn't really anticipated. When people thought of creatine deficiencies prior to the discovery of GAMT and CTD, they thought it was going to be more like Schwarzenegger problems, right? That you were just going to have people that didn't develop muscles, that were hypotonic, and cardiologists thought that there was not going to, that somebody with a creatine deficiency wasn't going to live. In fact, Thomas told the story multiple times that when he first presented this at a meeting, people doubted him because they thought that those kids would have died very young. And that the fact that they exist and have neurological deficits that predominate everything else was a bit of a shock. Again, going to show how little we actually know about this, about what creatine does. So we developed this model, and the first thing we did was knocked it out in every cell that we could, ubiquitous knockout. And this data is now 13 years old, but we did a pretty good job of developing a high fidelity model. I get asked a lot about that whenever somebody wants to develop a treatment for creatine or find a treatment for creatine deficiencies or something along those lines, and they ask me how good my model is. I'm not gonna be humble about this damn good model. We did a good job. What we see is a global cognitive delay. So I could get into the nuts and bolts about the Morse-Water maze, novel object recognition, condition freezing, and we'll talk about it a little bit. But the thing that you have to know here is we're not trying to model a specific aspect of human behavior. What we're trying to show is that they have delays in different things that we can actually map to different neuroanatomical regions of the brain. So the next question is how? How does lack of creatine cause these deficits? So we measured ATP in the brain and the muscle in the heart. We showed deficits there. We show that there's an increase in oxidative or mitochondrial respiration. And that turns out to be due to, if you look at panel D here from a paper, it's now 7 years old. I feel like I'm getting older every time I present these. But if you look at panel D, you can see the increase in this thing called citrate synthase. That's just a marker for total mitochondrial content. So the brains of these animals and the muscles of these animals just have more mitochondria. We've seen that microscopically as well. But it can't keep up with the ATP demand that is needed. So again, that's great, but then how? What we know is it does lead to changes in neural morphology. So this is, we crossed our creatine transporter knockout mice with these really cool mice. They were really cool when they were developed. Now they're starting to get a little whatever, but, and we show that the neurons in the hippocampus from these mice have fewer intersections, so they branch less. The idea is that if they branch more, they're forming more connections, they're forming stronger connections, you have an increase in plasticity. This is also found in a study by Alex Kwan that was published 3 years ago. They actually published theirs. We're still working on a few things in ours to get it sort of finalized. The other thing that we've noticed in our ubiquitous knockout mice to get to the house is there's change in synaptic plasticity. Still trying to figure out what else I need to add to this to get it published, but there are two aspects to this graph. First, on the left is what's known as long-term potentiation. This is thought to be it's thought to be the cellular basis of learning and memory. There's some caveats that people need to think about, but for the most part, people think that this is how, if you have this increased plasticity, it's learning. We'll leave it at that. So you can see that creatine transporter knockout mice have a deficit in this hippocampal plasticity. The other thing that we looked at was the sodium-potassium ATPase. So this is responsible for exchanging sodium and potassium in and out of neurons. The best analogy I can give you is if your body is a house, Sodium potassium ATPase is your HVAC system. It's the one that's using the most energy. So this actually accounts for about 8% of your total energy expenditure every day, is sodium potassium ATPase. So what we did is we applied an agonist to the sodium potassium ATPase, and you can see the creatine transporter mice don't actually respond as much to that agonist as the wild type mice do, which suggests that that protein is dysfunctional. And this is important because what it does is it sort of maintains your resting membrane. A lot of people think that it restores it. It doesn't. It actually is sort of just there. So like when creatine comes into a cell, it kicks out sodium, and then it has to pull back in. So it's important for a lot of those sodium fluoride exchangers to keep that sodium balance. So as you're pulling in glucose, you're pulling in creatine, it helps keep that balance. So it seems like this is disrupted as well. So we kind of get to the how on those, and then we kind of got stuck, sort of, so to speak. So the advantage to the mice that we made was that we can knock out the creatine transporter, and the same with large mice, is we can knock out the creatine transporter where we want to knock it out. We can kind of knock it out when we want to knock it out. And again, we're not going to get too deep into that, but I'm a developmental biologist basically by training. So the when is always the most important question to me. It always stuck with me as the most important question. So the first sort of real study we utilized these animals in was when. So what we did in this study, and this is from a former graduate student of mine, is that we knocked the creatine transporter out when the animals were born, or we waited until they were adults. And then we waited 60 days to let the creatine wash out. And we measured and we ran them through behavioral assays. And if you look at the top two panels, this is when we knock it out young. And you can see that there's a nice robust deficit in the Morris maze. When we knock them out in adults, not so much. They perform pretty similar to the wild type animals. Same with novel object. You get a nice novel object deficit in those early knockouts, whereas when you knock it out in adulthood, you don't get that same deficit. So this tells us, getting into the mechanisms, that creatine is important for brain development. How? Right? Well, the other thing is there are no deficits in conditioned fear. So this actually gives us a little bit of an insight as well, because the pathways that are important for conditioned fear actually develop embryonically. So if you think of the way the amygdala develops, those connections develop a lot sooner than postnatal day 5. They're actually more of embryonic day 14 to 15 in that range. So it kind of gives us that idea too, that we miss the critical window for that state-dependent learning. We actually got a lot of information about when out of these animals. So then we go into sort of how. And this is work from an undergraduate in my lab, actually, Adam Elzarka, who looked at what is known as, looked at EDU incorporation. So what happens is you give the animal an injection of this uridine analog, and every time a cell divides, that uridine analog incorporates, and we can actually stain for that analog. So all the red dots in the hippocampus and here in the dentate gyrus are cells that divided after we gave them that injection. So we can quantify that, and we did that at 3 different ages. We gave it at postnatal day 5, postnatal day 10, and 15, and then we waited 5 days and quantified it after it was done. So if you look at the middle panel here, let's see if I can turn this. So if you look at this panel here, you can see that there's a reduction in neurogenesis on postnatal 5, but an increase on postnatal day 10, and then a decrease again on postnatal day 15. But when you look at them when you break it into wild type versus knockout, what you see is that the knockout animals almost have a delayed neurogenesis, so that their peak is not at postnatal day 5 like the wild types, that there's a shift to the right, so to speak. And then in collaboration with Alois Bonzo, we looked at some markers, and he looked at similar markers in organoids, and that just came out in the fall. And we noticed that there's deficits in the genes that are related to neurogenesis. And just as a control, we also included the creatine transporter to show that it's knocked out, it's gone. But this shows that creatine is playing some sort of important role in brain development. Our next question is why or how, and what is it doing to keep that together? Now, it's known that mitochondria are important in neurogenesis and in differentiation from neural stem cells to neurons. So that's things that we're going to look at in the future. So the next question we had was where, and this was part of this work was from one graduate student, and the other was one that we've been working on lately. So we used these knockouts to knock the creatine transporter out in 3 different distinct neurotransmitter systems: serotonin, GABA, and dopamine. So we start with serotonin-specific model. We'll go through this slide real quick. There were no differences in the things that we normally look at: the Morse-Water maze, double object, conditioned fear. All of them were basically the same. One thing that we learned from doing a couple others tissue-specific or neurotransmitter-specific models, always include your ubiquitous knockout when you're running these studies, so that you know that your experiments worked. Because if your experiment didn't work, then what do you actually interpret the data? So we had a couple issues there as well that we had to go back and look at too. But we did try a new test in these animals, not new to us, and it's called learned helplessness. And in this is not a fun test for the mouse. So the mouse is confined to a chamber. We give them a battery of foot shocks. We wait a day, and then we open the gate, we deliver a foot shock. A mouse that actually learns this will stay in there for the whole time that foot shock is delivered. We deliver for 24 seconds, and they'll stay in there frozen the whole time because they've actually learned despair. Despair, not to anthropomorphize too much, but it's a despair-based learning. What's interesting is that our knockout mice, or ubiquitous knockout mice, and our conditional knockout mice didn't actually learn that helplessness. They escaped immediately, like they had never been shocked before. So we actually there's a control group where we don't shock, we don't perform this. We just put them in the cage, shock them, and see if they run over. They perform identically to an animal that's never been exposed to that paradigm. So that suggests that the serotonergic inputs are affected. And if we had not done this experiment, we would have just washed our hands of the serotonergic inputs altogether. But that it is affected. So, as we go through, it seems like any neuron that we actually look at creatine's important in the way they work. So then we go into the how, and again, this is work from Zuhair, who's now at Yale. And he looked at levels of TPH2, which is the main serotonin synthesis enzyme, and he looked at levels of MAO, which is the main serotonin degradation enzyme. And both of them were increased in our creatine transporter knockout mice. Asterisks didn't, or yeah, they did here. Looks like a lot, but you can see that they're both increased. And again, not that this is a target, but if you were looking, MAO inhibitors are something that's available. That is something that we could, in theory, in the future, think about testing in the mice to see if that pathway is truly affected and if it's responsible for those learned helplessness things that we see. So it's just one of those things as we keep going through, we always kind of keep an eye out for things that we can manipulate. Then finally, we looked at these we looked at GABA-specific knockouts. I'm going to get real quick about this. They had conditioned fear effects. And Laura's lab looked at parvalbumin, and she showed that they had effects as well, which is a subset of the GABA. We kind of did the same experiments at the same time with just a slight different flavor, which is always fun. It's always nice knowing that you're thinking the same way, because it's probably going the right direction if you're thinking the right. So anyways, but we have these state-dependent learning effects, the conditioned freezing. Again, this is a heavy amygdalar behavior, and the amygdala has a lot of GABA connections, so this matches. So again, it just kind of gives us this idea that creatine is almost important it's almost ubiquitously important, is really what it's kind of coming down to. And I'll show you, but there's a caveat coming up. The other thing that I'll show on this one here from that paper that we just published, the Cree mice actually caused a problem in novel object. So you got to make sure that you test your Cree mice too. Just things you learn along the way. And that makes it difficult for us to interpret it. That the GABAergic system could have contributed to. So then finally, we're going to look at these dopamine. And again, so one of the things I was thinking as we were going through, everybody was talking about hyperactivity. They're talking about this, and it's like, I've got analogs to most of these behaviors in this talk. So this is again from Zuhair. And he looked at a dopamine-specific knockout. And the first thing we looked at were the activity levels. So we see, and sort of appropriately, we see a mix, we see on and off hyperactivity in our mice. So we'll run a study with locomotor activity for one study and not see any hyperactivity at all. And then we'll run another study in the mice through the roof in their activity levels. And this is All of these mice are C57 black 6 mice. They're genetically identical. I mean, they cannot tell the difference between each other. They're so genetically identical. So there is something in there that is changing throughout. But we looked at hyperactivity across the lifespan of the animals and showed that the DAT-specific animals are hyperactive for most of their lives. And again, looking at the how, we see that this increase in dopamine in our knockout mice would be suggestive of how that's happening, is that you have this influx of dopamine. We didn't test these mice in the Orse-Water maze novel object of conditioned fear because we didn't necessarily think that the dopaminergic system contributed to that type of behavior. So what we really did on that point was, one of the concerns we've always had was the translational relevance of the studies that we do. You're never going to ask a patient to swim. You're never going to ask a patient to look at 2 identical objects and then 1 new object. Not going to shock anybody. I don't think any IRB is going to prove shocking anyone. But as we saw from Aurore, and we can ask them to make decisions. So we use the 5-choice serial reaction time test. So this is based on the continuous performance task. Measure attention, processing speed, and impulse control. They are required, get to it. The light comes on, mouse makes a decision. If he makes the right decision, he gets strawberry milk. They love strawberry milk. So good reward. So there are a bunch of mistakes he can make. He can pick the wrong hole, he can go early, he can completely omit. And we measure all of that. So we use the brain-specific knockouts because the one caveat is that you have to food restrict. We were a little afraid to food restrict the ubiquitous knockouts. But, and I showed this data at this, supposed 3 years ago, we got a really nice clean phenotype out of these animals, and they increased the amount of emissions, so they trials that they just skip. So if you think of ADHD, there are different types of ADHD. There's there's an emission type, so we've got that. They also made more mistakes. So we actually measure mistakes in 2 different ways. We look at the total correct, and we look at accuracy, which is correct plus incorrect, or correct divided by correct plus incorrect. So they're less accurate and they make fewer correct decisions. They're also slower to make correct decisions and the reward. So this is a good model, a good translationally relevant model to test this. But again, how? So we went back to these dopamine-specific knockouts, and really surprisingly, because the systems that control attention are dopaminergic. When you think about drugs that treat ADHD, all of them act by causing an increase of the release of dopamine. So we went to these dopamine-specific knockouts, and we didn't see any differences. So that's sort of curious. There are no differences in latency, no differences in omissions, correct anything. And if anything, the dopamine-specific, or the dopamine Cree mice that we use to generate these knockouts have a little bit of deficit themselves. But interestingly, when we gave the brain-specific knockouts amphetamine, it improved their performance. So if you look at, so this is a Z-score, just basically showing you how much difference it is from their baseline test. There are different directions that show improvement, but if you look at the purple bars, you can see that the accuracy improved, the number of correct improved, the correct latency went down remarkably, and the number of omissions dropped. So there's something going on there. So when we're looking at the mechanism, when we're looking at how, we know that there's something with dopamine, but it's not from the neurons that are releasing dopamine. It has to be something after that. So now the next studies that we're sort of working on is looking at, well, there's 2 different ones, is looking at the neurons that receive those signals in the striatum, and looking at, again, getting at the how, what specific dopamine pathways are disrupted, and what neurons receiving those are disrupted. So we're using, this is fairly new data, that we're using what's known as DREADS. This just basically allows us to turn on any neuron that's red by giving a drug called CNO. That's all you really know. And here's just proof of concept. We put them in a locomotor, we give them CNO. It basically looks just like when we give them amphetamine. The activity levels shoot up through. So what we're doing here is isolating one nuclei. So if you look at this, that's all the nuclei that basically are dopaminergic neurons. What we're doing is trying to isolate the ones on the interior part here, not the tails. And looking at and we're actually going to do the tails as well, but that's where we're at right now. So that's sort of our next steps on that, to look at the mechanisms that are really underlying these deficits, and showing that we can do this still through behavior and not getting to some reductionist thing where we're looking at the phosphorylation of one protein, or we're looking at, something that's so devoid, so far off from what we actually care about, that we then have to do a bunch of different studies to actually show it. It's main output of the brain is behavior at the end of the day. So that's really where we want to sit. So in summary, using our conditional knockout models, we've shown that early life creatine is important for cognitive function, and that basically every neuron that we touched, the behavior that it's responsible for is disrupted. So it shows that, again, going into that, and the reason we really wanted the neurotransmitter specific is because of this problem of getting creatine into the brain. If we have to target it to certain areas, then maybe we target it to certain areas. Maybe we overcome some of the things that we see when we try to use, say for gene therapy, we try to use these big banger promoters, and it makes too much, or we, whatever else it is. But it gives us a chance to maybe, in the interim, before we find something better, not let perfect be the enemy of good. So so sort of as I was finishing this, what limits our ability to understand these mechanisms? The biggest thing in the way is the rescue, is the fact that we can't get creatine back into the brain. A lot of times limits how much we can actually show that creatine is responsible. So necessary and sufficient. So we can't necessarily answer those questions unless we can reintroduce creatine into the brain. That's really probably the biggest roadblock that we have. Hopefully the development of AAV vectors that people are working on, or other therapeutics, will help us advance these studies, more importantly, provide treatments. But I mean, it really is one of those areas, like when Lars suggested the mechanisms thing, it just really made me think of how far we've gotten in answering these questions and how much further we have to go. And then finally, since we're talking about non-invasive measurements for the day, this is a recent development from our lab. I guess you could say we actually have someone in neurology that's developed a small animal MEG, and we were able to put our mice through the MEG. And we've got 5 mice so far, and I don't know anything about the MEG. So this is Greek. But I know that he was very excited when he sent me this slide. He was, and you can clearly see that there's a difference between the wild type and the Creatine Transporter mice. What that means, I'll find out by June. So, it definitely is something that we could test out and use this again to start looking at some mechanisms where maybe we can put them through some learning paradigms and simulate those learning paradigms in the MEG and see if it changes the way that those waves, the magic that he does. So again, it looks cool. So with that, I think I'm done. Yeah, that's it. So happy to take any questions.
Go back one slide. The first line, a true test would be to see if the molecule in question can reverse the phenomenon. If you had AGAT mice, so no complications of guanidino acetate, do you see the same phenomenon due to lacking creatine in the brain? Mm-hmm. And do you see that it reversed?
So that's a wonderful question. We have AGAT mice, and we are working on trying to give them creatine. And I actually looked before I came up here because I was thinking about that. Let's see if I can.
Do you keep them on creatine-free chow?
We don't keep them on creatine-free chow, but I'm going to show you real quick. This is real. Oh wait, so I actually looked at the distribution of wild-type heterozygous and knockout AGAT mice that we actually have. So we've generated about 300 mice from this colony. It's 50% heterozygous, 35% wild-type, and 14% knockout. So we have a shift that suggests that AGAT in mice may be embryonic lethal, that we're not generating those mice. So that's been a big hassle, is that we've generated 300, and we don't really have enough mice to actually do the studies yet because we're not getting the baseline mice that we really need to do the next steps after that. So, but yes, that's why we got the AGAT. That was the main reason, is because we didn't have a good system in CTD to do that rescue. And, and hopefully with the AGAT mice, we can actually test some of these. But we still have a lot of homework to do as far as making sure that the AGAT mice have the deficits that the Creatine Transporter Deficient mice have. So that's one of those due diligences that we need to do at some, as we can get animals. But yeah, there's definitely, AGAT's different from what I've seen so far in mice. It's just a little bit different. So even when we supplemented the dams with creatine, the litter distribution was still a little off. So it's definitely been a more difficult study than everything with creatine is more difficult than we thought it was going to be to start. So it is, it definitely was a little bit surprising that we're having such a problem generating these mice. So, but yes, you're thinking the right way.
I have a question. I don't know if there are questions from home.
No, we're good.
So the very first question is about when did you test the animal when you did the deletion of P5 versus P60? How long later when they tested the same? So is the age or the time that you are depleting the creatine?
It was the same amount of time without the creatine transporter. So 60 days. So P5 animals were tested at P65. P60 animals were tested at P120. So we kept the time without creatine because, I didn't show it in here, but the other thing that we kind of showed with that study is that the decay rate of creatine in the brain is roughly 3%, like we always thought it was. Is that it took 30 days to really clear the creatine out from the brain. So then we gave them, can't really test a P35 mouse in a lot of different tasks. So we gave them till they were adult. So, and then we just, it was the same amount of time with creatine each time. So, yeah.
And the deficit, the onset of the deficit for the different cell type, do you see different time of onset or they're all?
We haven't gotten too much into the age of onset. So we basically just go once they hit adulthood, we test them. The only study that's the exception of was the dopamine specific, because we were actually testing for something kind of completely different, but it came back to this is that we were looking at motor function. We wanted to see if they developed any sort of dyskinesia as they got older, because creatine had been implicated in Parkinson's disease and a bunch of other stuff. And we were just trying to see if they developed motor deficits faster than wild-type mice would. We didn't actually see any differences in that. And we carried ubiquitous through there too, and it didn't seem like there was much of a difference. But that was the goal of the dopamine study sort of from the beginning. But then we kept those mice around to do the 5 choice. So.
And your choice of choosing serotonin or GABAergic or dopaminergic was because they have a higher metabolism? What was the?
Usually it was
like a relationship and you think like, oh, these are more sensitive because they
so the GABA was definitely because GABAergic neurons tend to be bigger energy hogs than the rest of them. Glutamatergic, we were a little concerned about the balance of glutamate GABA and thought maybe we would have an epilepsy problem with the mice. But serotonin we selected because it had been heavily implicated in learning memory, especially developmental serotonin. So, serotonin release during early brain development is really important to help develop those hippocampal connections that then you use later in life. And some of that is, some of that's experimental bias. I studied developmental MDMA exposures and serotonin drug, so it's always been a little biased. But and then the dopamine we looked at because we were curious about the long-term effects of the lack of creatine transporter in those dopaminergic projections. Sort of worried about a Parkinson's type or related dyskinesia disorder.
These mice, do they have seizures? Any of these 3 lines?
I have not. So I've tested ubiquitous knockout mice for 14 years or so. I think I've observed 3 actual seizures. I've had students testing these mice for that long, and they've only, it's a handful. It's not, but mice are different. Rodents are different. They don't necessarily go into tonic-clonic seizures. There's a lot of subthreshold seizures, and Laura can be much better at this because she actually ran the studies. The EEG stuff has not been one that I've ever been able to get a student on board with, but it is. Rodents are completely different when it comes to seizures.
Yes, so you study with the CTD5, they don't have seizures, and everybody struggles because the patient have it.
Without a doubt.
It can be challenging if you don't record them.
I have a quick question. So you show that in one of our earlier slides that the sodium potassium transporter can be less inhibited in the knockout. But you're looking at the baseline or the comparison, like the baseline, is there any difference because the creatine is absent, and does it already intrinsically change the level of the sodium?
So yeah, so we're measuring from the CA1 of the hippocampus there, and this is with a multi-electrode rate. So we're not going to necessarily get a real strong comparison. So if we haven't patch clamped these guys, so that would be the next step in that sort of thing. It's patch clamping and looking for responses. But looking from an MEA standpoint, there's a lot of variables that go into MEA recordings. So you don't necessarily go, oh yeah, this one was 1,000, was 1,000 millivolts, and this one was 800, and we compare the difference in that or the slope of the lines, because everything's a little different each day. So that's generally why we go from a percent baseline on that.
Another quick question is about the biochemistry of creatine. I don't know what is the downstream of that when you have a transporter deficiency where you have accumulation of the creatine. Does the downstream degradation pathway be affected in a certain way, or if you have a selective knockout in your different cell line, right, like GABAergic, and so on, do you see compensation of the other cell type that increase the uptake of that?
So like, are you talking about like cell loss of the of specific neurons?
Driving the expression of the transporter
so yeah,
cell types or other compensation?
So we did look at, in the GABAergic paper, we used ribotag mice to isolate the RNA from the GABA-specific neurons and then the rest of the brain. We didn't see an upregulation of the creatine transporter in the lysate from the whole brain. So it doesn't appear to upregulate it. So that's sort of the best data I've got to answer that question right now. And it didn't seem like we've looked at AGAT and GAMT expression levels a couple different times. Haven't seen many changes in that, if any at all. If there is one, I'm not remembering it. So, but we've looked at it multiple times and not seen changes between AGAT and GAMT. So I don't think there's really any compensation that's going on, at least from in our hands with our mice. Yeah. And as far as downstream, we don't know what's downstream.
How does creatine get dissipated in the body?
Oh, it breaks down to creatinine and then it's expelled.
Yeah, question? Thank you so much. Last but not least, Laura. Laura Barroncelli is a principal investigator at the Institute of Neuroscience of CNR in Pisa, and is the person who actually catalyzed all of this, brought us together, and hopefully today will tell us a little bit of her work. Yeah, thank you.
Thank you. So, good afternoon, everybody. And first of all, I would like to thank Michela and ACT for organizing this symposium to celebrate together the International Day for Creatine Deficiency Syndromes. I'm really happy to be here because my lab is strongly committed to the research in creatine deficiency syndromes, and I'm really proud to have a computer not working, okay, to work with the team really involved in the creatine community. So today I'm going to show you the progresses that we have made in two different lines of our research, which are very intermingled with each other. The first one aims to investigate potential disease-modified treatments for creatine transporter deficiency, and the second one aims to identify quantitative outcome measures for therapeutic development. So, as Matt mentioned before, our journey into the creatine research started with generating a knockout mouse model in collaboration with Cornelius Gross at the MBL. Our mouse model carries the deletion of the exons 5, 6, and 7 in the SLC6A8 gene, which encode for the creatine transporter. And what we found is that this mouse model has a very good phase validity. Indeed, when we measured creatine in the brain of these animals, we found a significant decrease in the levels of this molecule with respect to wild types at every time point tested, basically. And we also found that the endophenotype of this mouse model quite well recapitulate the clinical picture of the CTD patients because they show a global cognitive impairment as we assess using different behavioral tests, assessing for declarative memory, such as the object recognition test and the Morris-Water maze, and the working memory that we assess using the Y maze. They also show an amplification of stereotype behavior in the self-grooming and the rotor task, a decreased motor function, and finally, they show an epileptic phenotype made of spontaneous seizures, but also an increased accessibility to kinetic challenge that we have seen using long-term video EEG recordings of 24 hours, sometimes even 48 hours. Basically, the mouse model represents a very good testbed platform for testing potential therapeutics, but also to assess the ethological mechanisms that link creatine deficiency to the neurobehavioral alterations that we have found in these mice. And indeed, we started our research looking for some mechanism of CTD. And we first hypothesized that basically some cell population of the brain might be more vulnerable to the creatine deficit, so to the deficit of energy metabolism due to the creatine loss. And in particular, as Matt mentioned before, we focused on paravalvulinergic cells because they have a fast spiking behavior, so they are very high energy demanding cells. So we asked whether we could recognize a very specific cell pathology in this mouse model. And to make a very long story short, the answer is yes. Actually, we found when we looked at the brain of this mouse model that there is a significant decrease in the density of paravalvulinergic synapses, and this is associated to a functional disruption of paravalvulinergic cells, which is made both of a decreased firing frequency, a lower resistance to fatigue, and also an alteration in the kinetic of the action potential. So basically, this data suggested us that paravalvulinergic interneurons can be one of the main substrates of CTD pathogenesis. And to further corroborate this hypothesis, we also generated a conditional mouse model similar to what Matt showed you before, but in this case, the deletion of SLC6A8 was targeted specifically to paravalvulinergic cells. And what we have found is that these mice present the very same cognitive alteration and the very same hyperexcitable phenotype that we have found in inhibitory mice. So demonstrating that the lack of creatine in this specific cell population is sufficient for the determinism of the neurological phenotype, at least this one. We know that paravalvulinergic cells are important for regulating brain plasticity and also for regulating the brain synchronization, the synchronization of brain activity and the communication among different brain regions. So we reasoned that the alteration of PV cells could be mirrored into an alteration of functional connectivity between different brain regions, and that this alteration of functional connectivity could in turn translate into the neurobehavioral alteration that we found in the mice. And to test this idea, we started a collaboration with Alessandro Gozzi at the Italian Institute of Technology, and we leveraged the sensitivity of resting strength functional MRI to assess functional connectivity in the brain of these mice. And Caterina Montani, which was a talented postdoc in Alessandro's lab, basically performed fMRI recording in our mutant animals at 2 time points, postnatal day 40 and postnatal day 140, corresponding to an early and late pathological state of CTD progression, at least in the mouse model. And what she found is basically a diffuse pattern of hypoconnectivity in the brain of mutant mice. Indeed, the blue lines that you can see here represent basically the connection that between brain regions that show a lower synchronization and so a lower connectivity. And this is true both at P40 and P140. And you can see from the quantification here that the connectivity strength is strongly, basically only reduced in the brain of knockout mice. The only thing I want to point out is that the magnitude and the extent of this hypoconnectivity pattern is different between the two age probe, because we found that at P40 there is a very diffuse pattern of connectivity, which is mostly present in the cortex, with an involvement in particular of somatosensory, motor, and limbic areas, while at P140 the hypoconnectivity is more focal and weaker, encompassing the motor cortex again, but also subcortical regions such as the striatum, the thalamic areas, and the hippocampus. So basically, this data suggests that parvapinergic interneurons are a key factor in the pathogenesis of CTD. And of course, we would like to screen some compounds for testing their ability to reverse the pathological endophenotype of our CTD mice. And this is, well, somehow work in progress, because for now we are putting our main effort in the therapeutic field on gene therapy. And so we started this project, I would say 7 years ago by now, maybe, when we started the gene therapy consortium with ACD, and we asked whether the reintroduction of a functional copy of SLC6A8 in the brain of knockout mice could be able to reinstate creatine levels and to rescue or at least prevent the onset of the pathological phenotype in these mice. So we designed this plasmid with the coding sequence of the human version of SLC6A8 under the control of the JET promoter, which is here in purple, which is a strong synthetic promoter, which is commonly used to drive very high levels of gene expression in mammalian tissues. And I have also to tell you that we also have an HA tag at the 3' terminal of this gene, because of course there are no antibodies valid to test the presence of the creatine transporter in the tissues, and so we needed a tag to see where our transgene was expressed. So basically we packed this plasmid into AAV backbone, and our goal was to understand whether a single intraventricular administration of this viral vector into newborn mice was able to rescue the pathological endophenotype of knockout mice. And Elsa Gherardini, which was a postdoc, very talented in the lab till 1 year ago, started to do this experiment, so started to inject the animals with this virus. And at first, she collected the brain tissues at P20 just to see whether our approach was able to reinstate the expression of the creatine transporter in the brain. And we did that using the Western blot against the HA tag. And as you can see, actually, we succeeded to reinstate the expression of transporter, because the green band corresponding to the HA tag was present in the brain of AAV-treated mice, which is not visible instead in the brain of untreated mice. And in a separate group of animals, we also performed immunohistochemistry, again, against the HA tag, to understand whether there was a good biodistribution of our transgene. And also in this case, the answer is yes, because we found a diffuse expression of the transgene along the anterior posterior axis of the brain, even if I don't have a full quantification of this biodistribution. I can tell you that this is basically very similar to what we have found in the literature, and there is, let's say, a 30% of cells that can be transduced by our viral-vector. So these results prompted us to start, again in collaboration with Alessandro and Caterina, a multi-site preclinical trial in which we performed the intraventricular injection in newborn mice, and we tested at different time points and at the multi-level, so both with the imaging and behavioral testing, the effect of our treatment. The control mice in this case were animals injected with the same virus, but containing the GFP protein instead of SLC6A8. And first of all, we found that our treatment was able to increase a little bit, at least, the body weight of knockout animals, which is strongly reduced usually. And indeed, you can find here that treated animals display a slight increase in the body weight, both at P40 and P140. But more importantly, what we found is that the treatment with the experimental vector was able to attenuate the pattern of hypoconnectivity that we found in the brain of knockout animals. Indeed, in the very same regions in which we previously found an hypoconnectivity pattern, here we found, well, an hyperconnectivity, but because here we are comparing knockout animals treated with the GFP and knockout animals treated with SSCA. So basically, there is an attenuation of brain hypoconnectivity following treatment. This is true only at P40. So I have to disclose that at P140, we didn't find any effect of our treatment in this fMRI contrast activity. At the behavioral level, the attenuation of hypoconnectivity is mirrored by an amelioration of autistic-like behavior. Indeed, treated animals basically show a drastic reduction in the time spent grooming themselves, while rather unexpectedly, we didn't find any amelioration of the cognitive impairment, because both at P40 and P140, the impairment in the spontaneous alternation that we found in the Y maze was still there, even after the treatment with SSC6A8. And we also detected a slight decrease in the performance, a slight deterioration in the performance of wild-type animals treated with the experimental vector, suggesting that the overexpression of the creatine transporter in the healthy brain circuit could be detrimental. At the end of the experimental schedule, we also probed for creatine levels to check whether our treatment was able to rescue the creatine level, the level of this molecule in the brain. And of course, as expected, knockout animals have a significant drop in creatine levels in the brain, but there is a significant increase of creatine content in the brain of treated knockout animals, with about a threefold increase, which does not reach, as you can see, the wild-type physiological levels, but is still significant. And interestingly, this increase of creatine is somehow mechanistically related to the neurobehavioral improvement that we have found, because we detected the negative correlation between the levels of creatine in the brain and the time the animals spent grooming themselves. So since the time of self-grooming, the higher time of self-grooming is bad, means that if you increase creatine levels in the brain, you will have an amelioration of the phenotype. Okay? So basically, altogether, these results provided a proof of concept demonstration that gene therapy has potential application for creatine transporter deficiency, and we have now deposited this paper on bioRxiv. But of course, you can see that there is still much to do, because we have to definitely optimize our construct to maximize the beneficial effect, but also try to mitigate the potential side effects that we have seen in the brain of wild-type animals. And this is why I assigned the project of devising a next-generation gene therapy construct to a group of postdoc and PhD students that they are quite brilliant, and we also can count for this project on the collaboration with Stuart Cobb at the University of Edinburgh, who has a very great expertise in generating gene therapy construct for many other neurodevelopmental disorders. So we reasoned why that the, let's say, partial failure of the jet-driven approach could be due to two different factors. The first one is that, of course, as we have seen before, the increase of creatine that we got into the brain of knockout animals did not reproduce the physiological level of the wild-type mice. But on the other side, since we were not able to map the expression of our transgene in specific brain tissues, we can, brain circuits, we cannot exclude the possibility that we are expressing our transgene too much in some circuits where it can be detrimental, and not enough in other circuits, such as those made of pharmacogenergic cells that are more hungry of creatine. And it is worth noting indeed that our single cell RNA-seq analysis, basically allowing us to understand the level of expression of different genes in specific cell populations, told us that the physiological level of SLC6A8 are quite low in the brain of wild-type animals. Here you can see the direct comparison with, well, basically a random gene which is quite highly expressed in the brain. But you can also notice, even if the level of expression are basically zero, that there is some kind of heterogeneity across cell populations. So we think that our next strategy will point to have a more physiological level of regulation of SLC6A8 of the endogenous gene to see if we can reproduce the wild type expression of the gene. But I'm not going farther for this part because you know, we would like to protect the patentability of this approach, and I hope to give you some more updates in the next few months, optimistically. Okay, so as you have seen, one of our main goals is to find therapies for creatine transporter deficiency, right? But to get there, we also need a set of outcome measures that are, well, needs to be validated and that can tell us the efficacy of potential therapies. And so this is why in the last few years, we also focused our research on novel outcome measures, and we decided to focus on hemodynamic responses of the brain. And this is because we reason that the lack of creatine induces, of course, an alteration of brain metabolism that could alter hemodynamic responses, which are made, as Samar mentioned before, of the transient changes of hemoglobin oxygenation and the transient changes of the blood flow following the neural activity. So we used this very simple and totally non-invasive technique called imaging of intrinsic optical signal that basically was brought to the lab by Raffaele Mazziotti from the University of Florence, allowing us to visualize the brain activity of the mice, thanks to the capability of the red light to penetrate the skull. So this is totally non-invasive, and you can visualize the brain activity quite easily and quite fast, and also in a longitudinal way. And we decided to measure visually evoked responses of the brain because there is growing evidence, mostly provided by the lab of Michela in other neurodevelopmental disorders, that visually evoked potentials can be a very good proxy for testing brain activity more in general, and to test the disease severity and progression for neurodevelopmental disorders. So Giulia Sagona, which was a PhD student in the lab, now she's a postdoc, did this experiment. Basically, she performed iOS imaging at 3 different time points in wild type and knockout mice. And what she found is that the amplitude of the visual responses is significantly different between knockout and wild type. And the amplitude of the visual response can effectively discriminate between the two genotypes at any time probe. Thus suggesting that the cerebral consumption of oxygen can be a reliable readout of functional alterations in the brain of these mice. And more recently, she also recorded some heterozygous females, which are here in blue. And what she found is that the amplitude of visual responses in this case stays basically in between the amplitude recorded for wild-type animals and the amplitude recorded for knockouts, thus suggesting that the level of hemodynamic alteration could be modulated by the levels of expression of creatine transporter, and of course by the levels of creatine in the brain. So the first important feature of a biomarker is that it can discriminate between healthy and pathological condition, and so the iOS can do that quite well. alongside to test the possible correlation between the level of hemodynamic alterations and the pathological phenotype of these mice. Alongside iOS, we also did a neuropsychological assessment in these mice using basically 3 different behavioral tests that we previously used to characterize the pathological phenotype of these mice, which are grip strength for the motor function, the Y maze for cognitive function, the rotarod for serotype movements. And what we found is that actually, at least for the Y maze and the rotarod, there is a quite good correlation between the behavioral performance and the amplitude of our signal, with the higher being the absolute amplitude of the signal and the poorer being the behavioral performance of the mice. Thus suggesting that the level of hemodynamic alteration could be predictive of the severity of symptoms. We replicated the same experiment at P110, and the correlation here is less evident, but we think that this is due to the longitudinal nature of our experiment, because basically the same mice did the same behavioral tests at 2 different time points, and so they might have familiarized a little bit with the arena, and so the variability of their behavioral performance is lower. So this is why we are now testing a separate group of mice just at P110, performing behavior and iOS parallel. And last but not least, one more important feature for a biomarker is to be sensitive to the treatment. Because of course, you need to discriminate between pathology and healthy behavior, but this needs also to be modulated by a treatment that somehow is able to correct the pathological endophenotype. And so we tested the mice. We would like to replicate this experiment also with the gene therapy that I described before. But for now, we tested the animals after the treatment with cyclo-creatine, which I guess most of you are familiar with, which is a lipophilic analog of creatine that we previously demonstrated to have some partial effect in restoring the behavioral performance in knockout mice. And what we found is that actually there is an attenuation in the level of visual responses in animals treated with cyclo-creatine. So suggesting that iOS is not only predictive of the pathology, but can be also modulated by it. And more recently, we also had the opportunity to record some animals modeling GAMT deficiency, thanks to the collaboration with Mauro Magnani at the University of Urbino. And what we found is that basically also in this case, the absolute amplitude of the signal is higher in knockout animals with respect to wild type. And this is not surprising in our opinion, because GAMT mice present, again, a drop of creatine levels in their brain, and this probably triggers the very same compensatory mechanism, leading to an increased need of requirement of nutrients by brain circuits that is reflected by this altered hemodynamic response. But this can expand the validity of this biomarker also to the GAMT pathology. So now, of course, the question is, what is the translational value of iOS? And the answer is that is very high, because functional renal spectroscopy is basically the parallel technique that allows us to perform the same measurements in humans, the same measurement we have done in mice in humans. So I won't spend too much time on describing this technique, because Samar did a good work before. Let me just say that it's totally non-invasive, because in this case we have infrared light that can penetrate not only the skull but also the skin. And this is this is a cup-based measure, which is quite comfortable, not annoying at all, in my opinion. We can testify that now, and can be done both in adults and children. So what we recently 5 years ago by now, acquired a NIRS, F-NIRS device at the Celamaris Institute, which is the child neurological hospital where I'm working with in Pisa. And Elena Scaffei, which is a very brilliant child neurologist in the lab, started to set up the system with the recording of adults and children with typical development. We would like to do again visually evoked responses, but she immediately realized when we started to do this experiment that we couldn't use the same stimulus that we have used for mice, because the classic visual stimulus is made of a gray baseline and the checkerboard sometimes appearing, which can be very boring. We can use it. We can use it, of course, with anesthetized mice, but it's very, very boring for people. And so we decided to devise a novel paradigm for visual stimulation, which is based on blending the classic paradigm with the cartoon. Okay, so I would like to show you how the stimulus is done. You cannot. Can I switch on my speaker? Yeah. You will see. You can see that. Just for a second. Okay. The audio will be on. The cartoon will be displayed in grayscale, and you can see that even when the checkerboard appears, the blending procedures allow us to still resolve the character of the profile of the characters, and so you can still follow the storyline. And so I think that you can agree with me that this is definitely more entertaining than a gray screen, for looking at a gray screen for 10 minutes. So with this in mind, we started to validate our visual stimulus, because we didn't know at first if the cartoon could somehow affect the visual responses that we get in the brain. So we started comparing the visual responses obtained with the standard visual paradigm, so the gray boring one, with that obtained with the cartoon-based stimulus. And as you can see here, as expected with the standard visual stimulus, we can see that there is positive deflection of total in green, oxygenated in red, and deoxygenated in blue hemoglobin. And the same is true also for with the cartoon-based stimulus. And these two conditions refer to the fact that we tried to see what happens when we selected a priori the cartoon. So when I decide to, to look at the Lion King, or when the cartoon was selected by the subject. So, and basically we found that the response is very similar in both cases. So basically we can get the same reliable response even when you subject can choose your favorite cartoon. And we did the same experiment also in children with typical development. In this case, we didn't ask to them to see the boring stimulus, but we asked them to see 3 different stimuli with 3 different cartoons. But also in this case, as you can see, we have found a very reliable visual response. And this is the quantification of what we found. Basically, the response, the amplitude of the response is independent from the cartoon chosen. And the same is true for the contrast, because basically we can show the cartoon at different contrast and the amplitude doesn't change. And this means that you can show the cartoon at a very high contrast, which make it even more entertaining because you can follow the storyline even better. The only thing I would like to underline is that the amplitude of the visual response is different between adults and children. And this is not surprising because of the progressive thickening of the skull, because children always have a bigger amplitude of the response with respect to adults. And this is something that you have to keep in mind well, in a minute I will show you why. We also tested the assessed the test reliability of our approach. For now, we have 2 groups of people. 27 of them were asked to replicate the same experiment at 3 different time points. So the T0, and then the T1 is 5 minutes later, and the T2 is 8 weeks later. And the second group is a long-term experiment in which 23 people did the experiment 2 times during the first visit. Again, time T0 and T1 5 minutes later. But the second the third experiment was done 2 years later. And these are the results only for the amplitude of total hemoglobin, but we have basically the same data for the other metrics that we have measured. And you can see that at least using the aggregate analysis of individuals, there is a quite good stability of the signal. We still have to further analyze this data to see what happens with individual traces, but this seems promising about the reliability of the signal over time. So let me show you what we have done so far for creatine deficiency syndromes. We enrolled the CTD individuals that we have at the Samar Institute. There are not so many. In total, we recorded 6 patients and a similar number of controls. But when we did the analysis, we realized that we had patients over 18 years of age and younger patients. So we decided to split them into groups, of course, decreasing even more our sample size. But this was unavoidable because otherwise we would have confounding effect on the amplitude due to the age of the subject. And here you can see that basically the recording of visually evoked responses is feasible. Here you have in red the response of the positive deflection of total and oxygenated hemoglobin in CTD patients, which is, well, similar to what we have seen in controls. In gray, we have the response to the blend, so the baseline cartoon, which is instead basically flat. This is the same for adults, which is, well, the quality of these recordings is definitely worse, but also in this case, you can see that there is a nice deflection of oxygenated hemoglobin and no deflection in case of the baseline. But more importantly is the comparison between the response elicited by the checkerboard between CTD patients and controls. And you can see that even if we have a very low number of subjects, there is a tendency towards an increase in the amplitude of the response in CTD, both in children and adults. Basically, possibly replicating what we have seen in the mouse model. But of course, you know better than me that these disorders are quite rare, so we need more subjects to have conclusive results. And this is why I'm very happy that thanks to European fundings, BCH funding, we are able to set up this multi-site study involving not only the Samar Institute in Pisa, but also the Hospices Civils De Lyon with the group of Aurore Curie, the BCH with the group of Michela, and NIH with the group of Samar, Rahhal, and Danny Porter. And this is very important because hopefully will allow us to reach the right numbers to demonstrate the robustness and the validity of this biomarker. And so basically this is it. This is the list of my collaborators and funding agencies that made this research possible. And this is the room that we set up and during these days here at BCH for starting FNIRS recordings. Basically the system is up and running, and we are just waiting for the IRB approval, and then we will be ready to start the recording. Thank you.
Okay, any questions?
The question about so that the creatine is created in peripheral, in liver or kidney and so on. So I'm wondering if the transporter actually is needed in those peripheral sites to transport it to the circulation and then go to the brain. If it is, then the AAV or gene therapy strategy, would that be useful to target those peripheral organs besides the brain?
Yes, one of the main sites of creatine synthesis are the liver and the kidney, but without any transporter in the brain, you cannot have the creatine gone there. So if you don't target just the brain, you cannot.
So my question is actually not peripheral only only targeting the peripheral, but actually both sides.
Okay, yes, of course. Yeah, of course. We try to use viral vectors that can be delivered systemically, but for now we had a lot of toxicity at the level of the liver, so we couldn't go farther. And this is probably because, again, the overexpression of SLC6A can be toxic very, very early. So basically the mice were dead after weeks, so we couldn't test them.
You actually measure the transcript expression in the brains after you gave the viral vectors?
No, we didn't. We would like now an in situ hybridization study and also a study with a knock-in reported mouse model to understand the pattern of SLC6A expression in order to compare our expression using yeah.
I understand, brains are valuable.
Yeah.
One of the lines of that, one of the things that we've considered actually are doing is using a brain-specific model instead, injecting the virus into there, because one of the things that I'm worried about, and even after talking in the gene therapy consortiums, is blood-brain barrier problem. It just is a good proof of concept if we left the blood-brain barrier intact in theory, brain-specific, injecting the virus. Have you considered that or tried that yet?
Yeah, of course. We decided to start with the ubiquitary mouse model because in our hands, at least, the phenotype of this model was more severe. Because, for example, in our condition, mouse targeting only the brain, we didn't see any autistic-like feature, and also the excitability was a little bit lower. But yeah, sure, the brain specific could be another option.
Things we wrestle with, right? It just it's just that's.
Thank you so much for that is somewhere in the cyberspace with us to the end, and I hope this is only the first of a series of meetings. And maybe next time we will show what we have recorded here and maybe this summer in Utah. So thank you so much to the speakers, Aurore, Judith, Irina is here, Samar, Audrey, thank you so much. And again, let's collaborate and make this happen, okay? Thank you.